universe is marvelous. Just look at the sky. Huge planets, bright stars, vast galaxies, massive clusters. It just fills us with tremendous amazement. In the last century, our exploration of the cosmos has reached unprecedented depths. From the first echoes of the Big Bang to the accelerating expansion of space, from dark matter and dark energy to ripples in space-time itself. Yet, with every answer, deeper questions have arisen. How far are we in understanding our universe? What lies at its beginning? Are there limits to knowledge, observation, and even comprehension? Is the astonishing order of the cosmos merely accidental? Or does its beauty, fine-tuning, and mathematical elegance point toward a deeper intelligence and purpose, as some of the greatest scientific minds have reflected across generations? To explore these profound questions, Bhaktivedanta Institute invites you to an extraordinary voyage through our cosmos, where some of the world's most brilliant scientific minds will share their insights and discoveries, including Andre D. Linde from Stanford University, John H. Schwartz, theoretical physicist, Caltech, USA, Wendy L. Friedman from the University of Chicago, Ofer Lahav from University College London, Avi Loeb, Harvard University, USA, Pankaj S. Joshi International Center for Space and Cosmology, India, and many more leading thinkers from across the globe. This is a space for rigorous science, open inquiry, and meaningful dialogue, where curiosity meets humility. Welcome back to your own astonishing home, the universe.
So, good evening everyone, and a very warm welcome to all our guests, speakers, faculties, and all our participants for joining us today from across the country and abroad for the Golden Jubilee lectures on Voyage through the Cosmos, history, models, theories, latest images, and foundational issues in understanding the universe. My name is Dr. Roshan Tiwari, and it is my privilege to be your host for today's program again. Today is the 5th day of our lecture series, and our lecture series began on 16th of March, Monday, and will continue until 22nd of March, Sunday, in online mode. So the lecture series is organized by Bhaktivedanta Institute as a part of its Golden Jubilee celebrations, marking 50 years of its service to humanity. So the timings of the lectures, as you can see on the screen, it is from 5 p.m. to 8 p.m. IST from Monday to Friday, and from tomorrow, means Saturday and Sunday, for 2 days, that would be going to be from 10 a.m. to 1 p.m. in Indian Standard Time. So please, just a humble reminder for all of you. So before we move to today's lecture, let me go through today's schedule briefly. So the first talk will be delivered by Dr. Luke Burns, Western Sydney University, New South Wales, Australia. He will speak on a very interesting topic, Fortunate Universe, Life in a Finely Tuned Cosmos. Then second talk will be given by Sri Vasudeva, President of Bhaktivedanta Institute, who is an alumnus of IIT Kanpur, and he will be speaking on very intriguing topic, does universe have a purpose? And the third talk will be delivered by Professor Frank J. Tipler, Professor of Mathematics, Tulane University, USA. And he will be talking on the universe, its beginning, its end, and the role of humanity in universal history. So before we move further, I would like to remind all our participants to please scan the QR code shown on the screen, and also the link of the Google Form link for submitting the question will be shared in the chat box. So do click on the link and submit your question during the lecture or after the lecture, anytime. So now it is my great pleasure to just give a brief introduction of Dr. Luke Burns. So Luke Burns is a physicist at Western Sydney University. He does research in the fields of galaxy formation and cosmological fine-tuning. Holding a PhD degree from the University of Cambridge, he utilizes numerical simulations to explore the evolution of matter in the cosmos. He is widely recognized for his work on the fine-tuning of the universe for life, investigating how minute variations in the fundamental constants of physics would render the universe uninhabitable. Dr. Luke Burns and Professor Kieran Lewis are the authors of the Cosmic Revolutionaries Handbook, A Fortunate Universe, Life in a Finely Tuned Cosmos, with Cambridge University Press. So with this brief introduction, now I would like to invite Dr. Luke Burns. Sir, please, the stage is yours.
All right. Hello, everyone. Hopefully you can hear me. Hopefully I'm not too loud.
Yes.
So let me share my screen, share my slides. Hopefully that's looking good for everybody.
Yes, perfect.
Wonderful. Okay, so thank you very much for this invitation. I want to say a special well done to the organizers. I'm quite happy to be in the company that I'm in. There's some really excellent speakers who they've got lined up for you, so I'm very glad to be amongst them. So my topic for today is a fortunate universe, life in a finely tuned cosmos. It's been my experience that whenever I talk to any audience that I get up in front of, and literally 2 days ago, I was in front of some high school students in Australia, and the same thing happened. Whatever audience I'm in front of, whatever topic I want to talk about, someone will always ask about life out there in the universe. So the scientific picture we have of the world around us, we want to know where we fit in. And is there other life out there? Is one of the questions that comes up in connection with that. Now, that's not quite my topic here. My topic is definitely about life and how we fit into the universe, though. But let me start somewhere else. I have the great privilege of being an astrophysicist. So uh, one of the wonderful things about being an astrophysicist is that the thing that we get to study, the universe, is an astoundingly beautiful place. Every new picture from this one from the James Webb Space Telescope, or from Hubble, or from any world-class observatory, or even a backyard telescope, is just mesmerizing, and it never really wears off. You never get bored of the universe, even when you're a professional astrophysicist. But what's wonderful about my job is that, as well as being able to appreciate the appearance of the universe, my job is to dig deeper underneath to understand why it is the way it is. So what you're seeing on the screen now is the center of a galaxy lit up in infrared radiation from dust, and you can see the sort of gravity pulling things together, the swirling motion of a galactic disk that's spinning around. You see holes in the gas of various sizes. The job of not just an astronomer to sort of take the data, but as an astrophysicist to try and understand what's going on here, is in the mold of the way that physics tries to explain things. So physics tries to explain things using three basic ingredients. First, the laws of nature. How does the stuff of the universe change and evolve? So, for example, gravity tells you, let's say Newton's law of gravity, for example, it tells you how things with mass accelerate each other, and so pull on each other. The laws of nature we know about, the sort of best laws we have, are all like this. They don't tell us how the universe is, they tell us how the universe changes. And that's quite important because it leads to the second factor there. If you want to know how the universe is, the laws alone won't tell you. You have to give them a starting point. You have to let them get their teeth into something. You have to, whether it's the initial conditions of the universe as a whole or just the system you're interested in, you have to give them a starting point from which to change. Um, it's a bit like the difference between if I were teaching you the laws of chess and I told you how each piece can move, you know, the bishop moves diagonally, for example, that alone isn't enough to set up a game of chess. I also have to tell you where to put each of the pieces at the start on the board. So physics explains by laws that act on initial conditions, but there's one more ingredient that sort of fits into the laws. What we find when we write down the laws of nature, the equations that describe the universe around us, we find that we need to put numbers into those equations. Now, usually the whole point of having an equation of the law of nature is that you get numbers out of the equations, because those are the predictions of the model that you have. To have to put numbers in is a very different thing. These are called the constants, sometimes the fundamental constants of nature. So for example, you're hopefully all familiar with electrons. The mass of the electron is, by some reckoning, one of the fundamental constants. So there is no equation that we have where you can sort of take that equation, solve the equation, and out of the equation comes the mass of the electron. We have to put that number into our equations. Now, we're perfectly capable of measuring that number. We know what it is. You can go and look it up. It's some very small number in any sort of normal human-sized units. But the point is, it's an assumption that we bring into the equations. Now, these, with one eye on the fact that we're going to ask the question about where we, as life forms, where we fit into all of this picture, it's important to know that these constants do play an extraordinarily important role in the way our universe works. So, for example, if you're familiar with the standard model of particle physics, you'll know that there is a bunch of fundamental particles, and you and me and this computer and everything we see around us are made fundamentally of three particles: up quarks, down quarks, and electrons. What our universe is capable of doing is taking those three basic building blocks, only three of them, and thanks to the forces that can hold them together, it can build up structure and complexity. So, for example, you probably know all this, but the protons and neutrons are made from quarks, two ups and a down, or two downs and an up. And then once you've got protons and neutrons, they will stick to each other and make the nuclei of atoms. And the electrons, thanks to electromagnetism, will go around the outside. How many protons you put in the nucleus tells you which element of the periodic table you are. So carbon has 6, for example, and there are 92 naturally occurring elements. But that they don't just sit there on their own. If you put two hydrogen nuclei and an oxygen nucleus close to each other, the electrons will orbit in a complicated way around that whole sort of Mickey Mouse shape, holding together all of the pieces, and that's a chemical bond. Our universe is very good at this. This is DNA. If you put these particular elements, hydrogen, oxygen, nitrogen, carbon, and phosphorus, in that particular order, you can literally write code. You can put the code for how you make a human being. Now, at this point, we're moving beyond physics and we're well outside of my expertise, but I'm told that the code will tell you how to make proteins. Those proteins you can put together to make cells, and if you put enough cells together, you can make small people, so I'm told. So if you go right back to the start of this story, there's the electron again, there's the up quark, there's the down quark. Their masses are right there at the sort of foundation of the building blocks of everything that we are made of. The reason this is particularly important is because if you started changing those numbers, you wouldn't just make a scale model of the universe. You wouldn't just make everything a little bit heavier. And there's an interesting reason for that. So the question we're going to ask now is, well, given that we don't know why these numbers are what they are, these masses of these fundamental particles, and a bunch of other numbers that describe the forces, we're going to ask, what if? What if the constants of nature had been different? Now, in total, there's about 31 of these constants that we know about that appear in the fundamental equations of physics as we know them today. So we can get busy trying to change them and seeing what's going to happen. So we've spent time talking about the electron, the up quark, and the down quark, so let's stick with those for a while. Here's a three-dimensional space. Now, if I ask you to pick three numbers to be the mass of the up quark, the mass of the down quark, and the mass of the electron, that's equivalent to picking a point in a three-dimensional space, right? Pick three numbers, or equivalently, think about this block in front of you and just pick a point in the block, and that will choose those numbers. Now, there are various reasons why we sort of cut off sections of the block. Up the top, you get very massive single particles, and up at the Planck mass, we would need a quantum theory of gravity to really know what's going on up there. So we'll just say, well, we don't know what's happening up there. Why don't we just cut things off at the top and at the back and at the sides, so we don't wander off into areas where we don't really know what's happening. There's another reason why it's cut off at the bottom, various sort of technical reasons in the standard model, but between those two limits, there are, as you can see, 60 orders of magnitude for you to choose from, and you can see where our universe is in the block. The sides of this, I should say, this is a logarithmic scale, so we're going up in factors of 10 on the side for up to 60 orders of magnitude. So what if we changed those numbers is equivalent to what else is happening in other parts of the block? If I go wandering off to the left or the right or the front to the back, what would happen in those universes? Now, that's a question we can sensibly ask because it just is theoretical physics. What would happen in a universe with laws A, B, C, and D? That's literally my job. Like, what are the consequences of this law or that law or these laws? Now, usually we ask that question with one eye on finding the laws of our universe. But in this case, we're saying what else could have happened. So let me give you an example. There's your block again, but I've carved off two sections around the sort of backside of the block. The reason you might want to avoid those is, whoa, my apologies, something's happened there. Heck, what did I just do? Hang on, my apologies. Oh, Keynote. Okay, tried clicking something, we're back. Okay, everyone stop panicking. So, it's very strange. Why can't I see the... All right, we're back, never mind. Okay, so here's your, no, back a slide. No, back a slide. Sorry, enjoy this. Enjoy this atom for a short amount of time before I go back a slide and then we play the whole thing again. My apologies. Okay, back, there we go. Remember what we're doing. This is like your menu. Like, what sort of universe would you like? And so those universes around the back of this particular block, I'm saying you should probably avoid those for the following reason. In most of those universes, the thing that you make out of up quarks and down quarks, which in our universe, protons and neutrons, but in some of those universes, it's actually something different. It's either three ups or three downs. The real problem is they don't stick to each other, right? And so let's see this wonderful animation again. This is where most of the special effects budget went. So here's a simple atom in our universe, deuterium, if you're interested. Proton stuck to neutron, electron going around the outside. It turns out with a reasonably minor change of the fundamental constants, right? Because there's all sorts of things being held together here. If you change those masses, you can very easily make a universe in which protons simply don't stick to neutrons. Or to put it a bit more precisely, the system where a proton is attached to a neutron has enough energy to unbind itself. It's unstable. Actually, with slightly different changes, you can make it so the electron doesn't go around the atom, it spirals into the nucleus and turns the proton into a neutron. These universes are very different from ours. Here's the reason. Here's the periodic table again. Here's the astronomer's version of the periodic table. It's got a nice little symbol on all of these elements according to where this element is produced in the universe. But if you've changed the fundamental constants in your universe, if you chose from one of those bits of the block that I carved off, what you've got is protons that don't stick to neutrons, and protons don't stick to protons either. And so your entire periodic table looks like this. It's one element. You can't make anything else. Anything else just falls apart. So in this universe, the only element is hydrogen. The only molecule is the hydrogen molecule, H2, and that is the end of the chemistry lesson because that's really all you can do in those universes. Once we start considering criteria like this, and they're very broad criteria, like will anything be stable? You know, can I put two things together and have them stick to each other? Once I start thinking through those criteria on very general sort of energetic grounds, usually, like this has enough energy to fall apart and this doesn't, what you find is that what remains of the block is this thin slice here, in which, in that gray area in the block, you get 92 naturally occurring elements capable of doing all the wondrous things of chemistry that we see around us. You can, for example, find online databases where every known chemical compound is there in the database. There are currently about 120 million of them. But if you're outside that little grey region there, that number drops from 120 million to 1 or 2, which is a heck of a change. It's quite a different sort of universe. So I mentioned how these calculations are done. One of the things that's relevant here is that these basic particles are also the building blocks, the fuel, I suppose, of stars. So let me give an insight into how this particular field investigates the sort of conclusions I've been talking about. So, for example, here's a famous paper in 1989 by one of my fellow speakers here, Mario Livio, who may have spoken already or may be coming up, I'm not sure, but co-authored this paper in 1989. And it relates to a process by which stars in our universe make carbon. Now, we are made of carbon, but that's not the only reason to focus on carbon as being an important element in the universe. There's this thing supposedly called carbon chauvinism, where we just assume that because we're made of carbon, it's really important. Not true at all. Carbon is extremely versatile. And remember, we have all the elements in the periodic table. We can do the experiment to see which is most versatile. For example, if you go across the sort of first, I guess the second row of the periodic table, and you say, how many different compounds could I make using that element, say boron, and hydrogen? So I'll give you, if you think about going across the periodic table, I'll give you lithium and hydrogen, I'll give you beryllium and hydrogen, boron and hydrogen, carbon and hydrogen, nitrogen and oxygen and hydrogen, right? And how many different compounds can you make? And for most of them, that number is 10 to 20. For nitrogen, it's about 70. And for carbon, it's about 30,000. Right, so carbon, just by a mile compared to everything else on the periodic table, is just phenomenally versatile. So it's rather important then, if you want a universe capable of doing interesting things, that your stars are able to make carbon, and ours make it via this process. You smash two helium nuclei together, they make a short-lived beryllium nucleus, but thanks to something called the carbon resonance, it hangs around just long enough for another helium to come in and make carbon-12. How would this process change if I change the fundamental constants of nature? That's actually quite an involved calculation, and thankfully for me as an astrophysicist, some nuclear physicists and particle physicists got busy and did it. So here is a series of papers. The Modern Theory of Nuclear Forces, a review of modern physics by these three particular experts, whose name will be coming up soon. They, having reviewed and being experts in the modern theory of nuclear forces, then publish a lattice effective field theory calculation where they build up a very good, very modern, very flexible and versatile model for the nuclei with that many protons and neutrons in them. So carbon's the last one there. Then they calculate this particular resonance, this way that a carbon nucleus can vibrate, which allows for the reaction to take place a lot faster than it otherwise would have. They look in more detail at this. They look in even more detail and consider the effect of the light quark masses on Big Bang nucleosynthesis. And finally, the viability of carbon-based life as a function of the light quark mass. Now, there's a lot of work being done there. And behind the scenes, the method here involves, these are some slides that I borrowed from Meissner, one of the authors there. It involves supercomputers doing an awful lot of work. But here's the summary of that. This again is from Meissner. The End of the World Plot is the rather entertaining title he's given it. But what you can see in the sort of yellowish, orangey, I suppose, squares, the light quark mass is tuned to 2 to 3% of its value in our universe. And electromagnetism is tuned to 2.5%. If you changed the masses of the light quarks by more than that, this process that makes carbon in our universe wouldn't work. It wouldn't make carbon, or it would turn too much carbon into oxygen. But there's some sort of caveats here. You've got to be careful about how you do this kind of work. Because as Fred Adams pointed out, if you change the light quark masses and some other constants in just the right way, you might end up finding another way of making carbon that's not this resonance. For example, if beryllium-8 were stable, you could just do it via the intermediate state. You wouldn't need this resonance at all. But it's still very interesting that we seem to be on a very sort of narrow strip of interesting universes. There's a look at what happens when you change the constants that inform the small things in the universe. We can also go to the large scale and look at the way that large scale structure forms in our universe. So here's a simulation. Now, this probably isn't doing particularly well over Zoom, but if you look around, I think this simulation is on YouTube and you should really go and find it. But this is what a supercube computer simulation of how we think galaxies form, done by the Eagle collaboration. And what you see here within an expanding universe is that, well, the short story is that gravity pulling things in is making the dense bits of the universe even denser. So you can see here the knots, right? The sort of intersections here of all these points are getting denser and denser. More and more stars and are forming in galaxies there, and really clusters of galaxies on this sort of scale. The overall pattern you see here is, for obvious reasons, called the cosmic web. So you have the bits where the galaxies are, these sort of voids over to, where you see the holes, and then the filaments running between them, which haven't quite decided which way they want to run. So this is the waterfall. So this is the way we think structure forms in our universe. This simulation, by the way, takes a supercomputer a month and a half to do, and so this really does, in terms of a video for a minute, there's an awful lot of very clever people's careers are spent in doing these sorts of simulations and then comparing them to observations and then trying to improve them. So the remarkable codes here. However, if we rewind back to the start, in our minds at least, and start thinking about changing some cosmological parameters, changing some of the numbers that describe the initial conditions of the universe that you see playing out here, it's again quite easy to make a universe which is a bit boring. For example, if you weaken the force of gravity, then overdensities in the universe just don't collapse. You don't have a universe which brings smaller lumps together into bigger lumps, or if it does it far too slowly. It's important to remember how much work our universe has to do on this particular scale. The average density of the universe, right? If you just sort of picked up a random bit of the universe and measured its density, how many kilograms per cubic meter, If you took that number and compared it to the density of, say, air in this room, what you would find is that the average density of our universe is much, much lower, about a billion times lower. So we really need that structure to form so that we get things like stars. But you also need to get the constants right in order to have stars be stable in our universe. So, for example, here's a video of the sort of structure of the sun. What's happening here, and actually astrophysical models of stars are remarkably effective and successful. The short story is that in stars, a gravity pulling in is matched by heat or thermal pressure pushing outwards. What's important in our universe is that it's a stable equilibrium. So gravity pulling in, heat pushing out. If gravity pulls a bit harder and makes the star contract a bit, it will heat up, and so the heat will push back even harder, and the star will return to where it is. If the heat pushes back too far and the star expands, it will cool off and gravity will pull it back in. So there's not just an equilibrium, a balance between the forces, but if the star tries to step away from that balance, it will be pushed back into balance in our universe. However, if you take those very successful models of stars and you start to say, well, what if I made gravity stronger? What's interesting is that it's very easy to make stars that don't return to order, that overreact and blow themselves apart. Anything big enough to burn is simply big enough to throw off some of its matter entirely and to stop being a star. If your gravity is really strong, or equivalently, if you start your universe off far too dense, what you will have is a universe full of black holes. And that's no good either. So much of the energy we see around us, the energy that ignited the sun, for example, in the first place, came from the collapse of matter under gravity. So if you start a universe off with black holes, you've sort of used that form of energy up already, and the universe is a much more boring place because black holes, well, they will collide with each other, but they won't do much else apart from just eating things around them. There's other ways to get the beginning of the universe wrong. At one point in the history of cosmology, up to about 30 years ago now, these we thought were the three options. The universe had a start. You see those three start points down the bottom. It then expands. You see all those three expand as we go upwards. But was it the case on the left that the universe stopped expanding and came back and crunched? Or the one in the middle you can see there, that it just sort of keeps decelerating forever, but never quite turns around. Or the one on the right, that actually it expands too fast for gravity to have much of an effect and just sort of coasts off into the distance. Those were the three options for what we thought the universe was doing, until about 30 years ago, where the universe threw us a surprise that actually it's a fourth option, which was always available in the equations. We just didn't think it was very likely, that the universe is in fact accelerating. A distant galaxy out there in the universe is not only moving away from us, it's moving away faster today than it was yesterday. Why is that happening? Well, as we looked around for an explanation, there seemed to be a good cause of this behavior at hand. Ordinary matter won't do this, but if empty space is full of vibrating and oscillating and doing quantum strange things, fields, even though there might be no particles there, which in practice means if you put a particle detector there, it would not go off. But if the fields are still there oscillating around, then some amount of mathematics later, let me just hand wave over all of that, we get a prediction that, oh, that energy in the form of these oscillations in empty space, that form of energy would make the universe accelerate in its expansion. However, this theory of dark energy, this particular theory of dark energy, mismatches our observations by an enormous amount, by 10 to the power of 120. In other words, if we just sort of thought, how much energy would there typically be over here, oscillating away in the universe? Well, an awful lot more than we actually see. So most universes, the sort of typical universe in which this is true, and we have very good reasons from particle physics to think that there are these oscillating fields in empty space. If you had these energies being as large as they seem to typically be, but negative, what would you get is a big bang that ends very quickly in a big crunch, in a tiny, tiny fraction of a second. But on the other hand, if they're the size we think they are, but not negative, which leads to a crunch, but positive, what you get is a big bang that very quickly just accelerates off into the distance, and you get an empty universe. In that sort of universe, the sort of scenario where one proton bounces off another proton would be extraordinarily rare. So that's a beautifully simple universe if you're an astrophysicist. You don't have to worry about stars, planets, gas clouds, galaxies. You don't have to worry about any of that sort of stuff. None of that happens. At the most, a proton will bounce off a proton. As long as you understand that process, and the electron bounces off electron, proton maybe collides with an electron maybe once in a trillion years. Once you've got those processes, that's all you need to worry about. The universe is beautifully simple. There is no one there, unfortunately, to see that. Our work, my co-author, Geraint Lewis, and a bunch of our colleagues, including those from the Eagle collaboration, part of our work is actually to use that code to flesh out this, what I've shown you with simple animations, actually in detail via simulations. So nothing's happening on this slide yet, relax. But when I hit play, on the left-hand side is going to be a universe which is approximately our universe. And the one in the middle is, what if those quantum oscillations in empty space were 10 times larger? Or what if they on the right were 100 times larger? Remembering that a typical universe, they might be 10 to the 120 times larger. So what you could imagine is, here's our universe 10 times larger, 100 times larger. You could imagine off to the right of the screen there, another, 118 panels. So using that same code that was used to calculate with a reasonable degree of success the way structure forms in our universe, let me hit play now. They all start with roughly the same initial conditions, but on the left, while structure forms and wonderful things happen like galaxies and stars and planets, you can already see over on the right what this increased acceleration does to the universe. Everything gets too far away from everything else. Structure doesn't form just because that process by which gravity brings things in gets shut off quite quickly. And that's only for 2 orders of magnitude more than in our universe. There's another 118 to go. This particular problem, right, it's called the cosmological constant problem. Now, there's a couple of different terms here: cosmological constant, vacuum energy, dark energy. For our purposes here, we can treat those sort of the same. But let me just go into a little bit of detail about why it's such a problem. First of all, it's actually a bunch of problems. It's several problems at once. So here is Einstein's equation of general relativity. This is what describes the expansion of the universe. The problem is, right, that one quantum field will add a very large term over on the right where the energy density is, the stress energy tensor. Every other field will also add another number on the right-hand side. When I say add, it could add or subtract. It could be positive or negative. So what's happening on the right-hand side, as a sort of roughly what's going on here, is, a whole bunch of independent processes, so far as we know, all the different fields of the universe, throw a number over on this right-hand side, which then gets added to, actually, there's one on the left as well, which we don't know why that would be what it is, but a bunch of numbers end up over here. All of them are enormously larger than what's observed, yet all somehow magically cancel out, and the universe doesn't blow itself to bits, and here we are. Each of those contributions is a cosmological constant problem, so it's really several problems. Secondly, general relativity won't help you solve this problem, because general relativity doesn't tell you what the universe is made of. It tells you how the evolution, especially the gravitational sort of dynamics of the universe, depend on its energy contents. it won't tell you what's in the universe. And so it won't tell you, oh, there's definitely no, extremely large quantum fields in there. Particle physics probably won't help because particle physics is blind to the absolute scale of these energies. Only gravity knows about the absolute scale. Particle physics only depends on the relative scale. Fourthly, it isn't just a problem at the Planck scale, so quantum gravity won't necessarily help. We know enough physics, and we've tested enough physics to know that this problem exists without having to know or even guess what's up at the quantum gravity regime at very high energies. Fifth, there are other forms of dark energy, other things that could make the expansion of the universe accelerate, but those don't erase the vacuum energy, and they could have exactly the same problem. Why are they so small relative to the value they could have had? Six, since 1998, we can't just say, oh, there is no accelerating expansion. That can't happen, because we know it is happening in our universe. And on a related note, seven, if cosmic inflation happened, which I haven't really talked about, but it's a very rapid acceleration of the early universe. If that happened, then a life-prohibiting acceleration is physically possible, so you can't rule it out with any sort of symmetry. Eight, there's a very clear connection to what I've called the anthropic limit, to life. It's very clear that if you completely blow the universe apart and no proton ever touches another proton, then you're not going to get life. Right? I don't care what your definition of life is. A proton in empty space is not alive. And nine, this calculation we do to say what quantum, what might be out there in the quantum vacuum is known to be correct in some environments. It's called the Lamb shift. The method we use for that, you can't just throw out that method because that method works. So we really are painted into a corner here that there does seem to be an awful lot more space for universes that do life-prohibiting things. So here's a summary. There's more cases that we discuss in the book, but of all possible values of the fundamental constants of nature, the subset that permits the existence of life seems very small. That's the sort of summary of what's going on here. Let me give you a brief overview of the way people have responded to this, and then we'll get to questions. My favorite response is this one. I'm not religious, but something weird is going on here. I find that very funny. The instinct here goes a little bit like this, right? At some point, hopefully this video is doing well over all of the internet, but it's a hummingbird flapping in slow motion. There's something really remarkable about the stuff that's in our universe that we know around us, right? The protons, neutrons, electrons, quarks, and all that sort of stuff manages to pull itself into the form where it can do the thing you're seeing on screen. I've been using this illustration for a while, and I think the internet heard me because it started showing me ads for this, trying to sell this to me, and I'm slightly tempted to buy one. The reason why this fine tuning it's unnerving because actually it's extremely familiar. We're very familiar with what's happening in fine tuning. It just seems completely out of place in physics. So why look at the thing on screen. Look at one of the, say, cogs, right, with the gears on the wheels. Why does it have exactly that many gears, cogs on the edge of the gear? Why is it exactly that size? Well, because someone thought out ahead of time that it would go exactly in that place on exactly this contraption and do exactly the thing it was supposed to do. That's the sort of thing minds do, and it's so obvious and so common, we don't really stop to think about it. But what's weird about fine-tuning is it seems that our universe at its beginning had certain properties so that later on it would make stars, planets, galaxies, and life. Now, that's not the sort of explanation you get within science, right? The things are as they are because of what's there at the time, and then the laws just play out. It's very strange to see the universe seeming to plan ahead. So what are the other options for explaining the way that our universe is? One of them is that we just need to do more physics. The laws as we know them have the fundamental constants as we know them, but new physics could come along tomorrow and show us that these constants, maybe they're actually dynamical quantities. They vary from place to place, but really the sort of grand hope here is that more physics will show us that these constants couldn't have been different, that we'll understand why they are exactly why they are, that we'll find that deeper equation that allows us to get the numbers out of the equation rather than having to put them in. That's a hope. At the moment, we don't know what physics will do tomorrow, so we don't really want to sort of prejudge that. There's a very interesting paper from Bernard Carr and Martin Rees from 1979, which makes the following comment just as the paper ends. It says, okay, I'm paraphrasing, maybe some deeper mathematical symmetry will explain these numbers and explain the coincidences between these numbers, but it would still be a bit strange if something as abstract as mathematical symmetry explained why the universe is capable of producing life. It would be weird if the only mathematically possible universe was one in which hummingbirds exist, for example. Another option which is discussed is a simulated universe. I mean, I make universes in a computer. Maybe ours is made in a computer. Maybe we are the product of a simulation in the universe upstairs, so to speak. Now, what's interesting about that is if our universe, remove the thought that maybe there's a programmer in the upper universe or whatever that is, but if our universe is fundamentally digital rather than analog, if you want to put it that way, there might be ways that we could observe that. And that would be interesting. Nothing's turned up so far, but it's worth thinking about. Finally, maybe we won the cosmic lottery, the multiverse. Now, you've already had some talks about this, I think, but the idea is very simple in terms of fine tuning, right? There's maybe out there's lots of other universes. They all have different properties. And if we went looking into them, we'd find that for these fine tuning reasons, most of them don't have any structure inside them. Most of them, for example, get large or very large and negative cosmological constants and just blow themselves apart. But there's no one around in those universes going, oh man, what went wrong around here? All of the people who are asking the question of why they're in the universe they're in are in a universe that's right for life. And so there's the explanation. Now, on one level, that's for me as a physicist, that's something I want a detailed model about. I want to go and do predictions. That's why we did those simulations I just showed you, to try and understand, try to test some of these models. I'm not sure whether it's going to answer that deeper question of why is there something interesting and rare going on around here? Because it seems like it might just push that question up a level, that a fine-tuned universe would just suggest a fine-tuned multiverse, and we still find ourselves face to face with a universe that's doing something interesting and rare. But that's the sort of where the debate is at the moment. Those are the live options. I'll leave you with the book if you want to dive into those anymore, and say thank you very much for your attention. I'm looking forward to your questions.
Yeah, thank you, Professor, for your wonderful talk. And also thanks for highlighting very important empirical study of this fine tuning, and also sharing some papers and simulations. So thank you very much. So now we have got a few questions from our participants. So the first question, so before that, I would like to request all our participants to please scan the QR code shown on the screen, and also the link has been shared in the chat box. Just click on the link and submit your questions to the speaker. So we will have our first question by Rajesh. So he's asking, how robust is the evidence for fine tuning? Could some of these fundamental constants be varied without eliminating the life? Do these constants drift with time?
There's a couple of questions there. First of all, a lot of effort has been put in to try to work out whether these constants drift with time, because that would tell you it's obviously not a constant, but that would be very, very interesting. Again, a lot of effort's been put into that. At the moment, there's no evidence that they change in a significant way. One of the ways you do that is by looking at the sort of furthest thing that you can see, which is usually a quasar out there in the universe, and see whether the relationships between the electron levels that we see in the emission lines, whether that's changed. So the reason why that's very useful is because if one of the fundamental constants changes, that immediately tells you there's something wrong with the laws of nature we think we have at the moment, the standard model, they have to be wrong because they say that they're constant, and so you can go ahead and book your ticket to Stockholm because that's probably worth a Nobel Prize, but nothing's turned up. These constants, as I said, there's 31 of them. I should say a lot of them, probably most of them on balance, actually, because they relate to parts of the universe or pieces of the universe that don't affect life, they actually aren't particularly fine-tuned. For example, a bunch of the constants relate to the properties of neutrinos, and all life really needs from neutrinos is that they don't bother us too much, which there's neutrinos from the sun passing through your body right now. So a lot of the case studies I've presented, I think are very robust. As I said, we've done simulations, the work of Fred Adams, particularly on stars. We've written some papers on that stars as well. The sort of papers I shared about the way particle physicists are doing things. Um, um, Actually, you're not the next speaker. The one after is Frank Tipler. Frank Tipler and John Barrow in 1986 wrote the sort of classic book on this, The Anthropic Cosmological Principle. A lot of those arguments back then were very back of the envelope, very rough order of magnitude calculations. But by now the field, like we're trying to answer these questions with the sort of best simulations we have. So I think in terms of the physics we have, a lot of the cases, as long as you're up to date and a bit conservative with the way you present it, are very, very robust. But we don't know what physics is going to tell us tomorrow. So it might tell us something entirely new about a quantity that we thought was a constant. So, yeah.
Yes, thank you, Professor. So next question, please. So this is question by Professor Lewis from York University. So Professor is asking that in chess, pieces can be captured and removed from the board. As a result, the game eventually ends. In the universe, energy conservation precludes any change in the number of particles. The game of the universe doesn't appear to have any rule that will make it end, and from symmetry, we can't talk of an initial position either. How can we know that the universe had a beginning if our interpretation of redshift is still debated?
Ooh, very interesting. Um, Sorry, I'm just going to stop sharing so that I can see the questions.
Okay.
Ooh, have I stopped sharing?
No,
I
no,
think I
it is
have.
there on the screen, sir.
Oh, okay. Okay. So there's a couple of interesting questions there. Yeah, very interesting. First thing to sort of drop a bombshell here in conservation of energy from what's called Noether's theorem follows from time translation symmetry, and the expansion of the universe means that the universe is not time translation symmetric, so actually doesn't conserve energy. More than that, energy conservation does not preclude any change in the number of particles. Particles are not conserved. Energy, even in the smaller scale where energy conservation still applies, um, that it doesn't imply conservation of particles. So, for example, I mean, there's a light bulb right above me. It's producing photons at a phenomenal rate, but it's not. There's no conservation law there. Every time electron goes between two levels, out comes a photon, and then you can just keep making those. So you've got to be very careful if you want to talk about the way what the universe is going to do next, because it's quite you've got a lot of work to do to try and work that out. The game of the universe doesn't have a rule that will make it end. Um, we can't talk of an initial position either. That's where I think there can actually be an asymmetry. There can be different things according to the models, according to the best physics we have. There can be differences about each end of the universe, the beginning and the end. It could have a beginning in time. There was, a point where there was no second worth of time before that point, but still be sort of eternally infinite into the future. How can we know that? Well, what we need is a theory about how the universe evolves that we sort of trust to take us sort of extrapolating back that way. We have general relativity, but for various reasons, we think that quantum gravity might have to replace general relativity at some point. Although, in 2 talks' time, as I said, you're about to hear a talk from a guy who doesn't think that, Frank Tipler. He might mention that point. You could ask him about it. Um, One final point there. How can we know the universe had a beginning if our interpretation of redshift is still debated? No is a very strong word there, but I want to say that, the interpretation of redshift as due to the expansion of space is very, very well established, does an excellent job of explaining what we see around us. My book with Geraint Lewis, The Cosmic Revolutionary's Handbook, will present that case if you want to see that one.
Yeah, thank you. Thank you, Professor. So, fourth question, please. So, this is question by Pradeep Kumar, Kendriya Vidyalaya Sangathan. Thank you so much for such an enlightening and profound lecture on the fundamental nature of our universe. If I may, I would like to ask, while your work brilliantly demonstrates that the physical constants are finely tuned to permit the existence of complex matter and life, do you believe that this tuning extends to the emergence of subjective awareness itself, or does the hard problem of consciousness requires a separate explanation that physics alone, no matter how finely tuned, might not be able to reach? Quite long question.
Yeah, so basically, does fine tuning shed any light on the hard problem of consciousness? I'd say no, it doesn't. Um, exactly what the universe needs to do in order to produce consciousness is just beyond me. I'm just an astrophysicist. I find the hard problem of consciousness to be, one of the things in life that you should really sit down and really have a very hard think about. Because especially for me as a physicist, I do these simulations, I write the code, I set it going and the unit and off it goes. I know what it means to say I have a sort of universe in the computer, and within that, it made a galaxy. There's some arrangement of things that I can say that's a galaxy. I don't know what it would mean for me to look inside the universe that I made in a computer and say, oh, it's conscious. It's having a first person experience. I just don't know what on earth I could possibly do looking at the universe I made to reach that conclusion. So, like I said, I don't offer any sort of conclusions about the hard problem of consciousness.
Yeah, thank you, sir. Yeah, it's really very hard. Yeah, thank you. So, next question, please. Yeah, this is question by Jagdishwar. He is asking, if the physical constants of our universe occupy a vanishingly small region of possible parameter space, as illustrated by the 60 orders of magnitude gap between the electron mass and the Planck mass, is the
Mhm.
fine-tuning problem scientifically meaningful without a well-defined probability measure over that space? And can such measure ever be empirically grounded?
Very good question. If you want to hear the voice of someone who's very skeptical about all of these, Sabine Hossenfelder is a name you can find. She wrote a paper in 2018 called, I think, Screams for Explanation. Anyway, it's basically saying no to the question you've asked. My response to that would be, when in science we want to weigh two separate theories, we've got our observations of the solar system, for example, and here's Newton's theory and here's Einstein's theory. Um, we need a way of weighing those two up. So at the end, we can say something like, well, given the data I have, Newton's theory is more probable, or Einstein's theory is more probable than Newton's. In order for that to be a meaningful statement, you need an idea of probability which doesn't just come out of the observations, which comes out of sort of the theories themselves. I think that's what Bayesian probabilities do. So there's this approach to probabilities where you treat probabilities not as descriptions, sorry, statistical descriptions of data, or even the sort of stochastic probabilities of things in our universe, but as degrees of support between one idea and another idea. And so, how much does the data support Einstein? Well, it's not like we have 100 universes and in 99 of them Einstein's rules. So we need a different idea of probability. That's the approach I would take. I've defended that in a paper called A Reasonable Little Question, if you want to go and look up that particular paper.
Yeah, thank you, sir. So we have few more questions. Is it okay? Are you
Yeah,
fine?
please, go for it.
So next question. So this is question by Bach, Bangalore University, is asking, can you rule out interaction between different universes? If not, are there any signature of such interactions?
We can't rule it out. So the thing to do with that is if you have a model for what interactions would look like, and if there were signatures of that, you would sort of run that model. In practice, however, once you start the sort of models we have, and they're quite hand wavy, but the sort of models, Andre Linde probably talked about them, where inflation produces a multiverse. Because you're relying on a process which expands the universe so quickly, this accelerating, inflating expansion, the bits of the universe, the sort of individual universes in the multiverse end up so large that it's very unlikely that you're near the edge of one. So there would be edges between, here, this universe has some property, and then just over there, there's, electrons are heavier or lighter or something like that. If you're going to have a working multiverse theory, there must be places like that. But in almost all multiverse models, the universe domains, the sort of individual universes, are so large that it's not a prediction of those models, or extremely unlikely on those models that we would be anywhere near the edge of the universe. So this is a real worry, because what it means is that your one hope of directly observing some prediction of the multiverse that maybe there is a different electron mass over there is almost got no hope according to the multiverse. You just won't directly see any other universes. So that sort of confirmation of your theory is almost certainly impossible.
Yeah, thank you, Professor. Next question, please. So this is question by Ritvik. Can you explain about Hoyle's state carbon resonance favoring the abundance of carbon in universe? What can be the explanation behind this?
So Hoyle, this is one of the first sort of most famous cases of fine tuning. If you just do a basic calculation of if I had a star full of helium at a certain temperature and I just let it go, how quickly would it make carbon? And you do a basic calculation, and the answer is extremely slowly. And so Hoyle thought, well, that can't be right because there is carbon in our universe, so there must be something else going on here. There's a way to accelerate these reactions if there's what's called a resonance in the carbon. There's just a certain way that it can handle vibrations and sort of live for a bit longer, so to speak. The maths behind this is part of quantum mechanics. It's sort of hard to explain, but that's the short story. On the basis of this, Hoyle actually predicted that resonance. He said, well, if this resonance isn't there, stars won't produce carbon. And so he called his friend Willie Fowler, who was a nuclear physicist, and said, look, I can tell you where to find a resonance in the carbon nucleus. And he was right. And he absolutely should have won the Nobel Prize for that. And it's ridiculous that Hoyle never won it. So then Hoyle said, this, his quote later on was, it looks, I'm paraphrasing it, but it looks for all the world like a super intellect has monkeyed with physics. Right, the properties of our universe were set up so that it would produce carbon. There's a little footnote there, as I mentioned during the talk, that there's other ways you could make carbon by, say, binding beryllium. But whatever the case, it seems that there's this sort of there's lots of ways to make universes in which there's not much carbon around, and ours is one that is able to make plenty of carbon. So why is that? Is the question of why our universe is fundamentally the way it is. Maybe there's deeper physics. Maybe we got lucky because we're part of a multiverse, or maybe someone's thought it through beforehand before making the universe.
Yeah, thank you, Professor. So we will take a last question. This is question by Dr. Aniket Chowdhury. Given that the cosmological constant must be fine-tuned to 10 to the power 120 for galaxies to form, the strong force coupling must be fine-tuned for the Hoyle resonance to produce carbon. And the electron mass must sit at precise point in a 60 orders of magnitude parameter space for stable chemistry. Are these independent fine-tunings are symptoms of single deeper constant whose mathematical structure we lack the conceptual vocabulary to even pose as an equation?
Right, a couple of things there. I mentioned my paper, a reasonable little question. The 120 orders of magnitude, there's ways to soften that, just to do some technical stuff first. If you start varying other parameters, there's ways to have larger cosmological constants and still get life as long as you can do some other things. But the short story is you do have these interesting fine tunings. I should say the electron mass one is probably actually about 17 orders of magnitude. The 60 orders of magnitude was just the possibility space. Are they independent? Well, what we're doing here when we do fine tuning is taking stock of where we are, right? Here we are. We have a really remarkably successful set of models that tell us about particle physics, tell us about the expansion of space, and they're very interesting and very useful. And now we ask the question, all right, well, is there anything sort of rare or interesting or special or remarkable at the way the universe is that we see around us? And the answer is, well, yeah, most of the other ways that we could sort of model a universe, it doesn't do the interesting stuff that ours does. Is there some ultimate constraint that's deeper and behind the scenes that might explain it all? Maybe. The weird thing about that would be, as I said, that paper by Bernard Carr and Martin Rees, it would be a little bit strange if, it would just be another deeper coincidence if mathematically beautiful symmetries and what a universe needs to do to make hummingbirds were the same criteria. That would be rather strange, don't you think? Although it's harder to sort of quantify, but there's still, even if there was a sort of deeper explanation in terms of symmetries, there'd still be something strange and unique and weird going on around here.
Yeah, thank you, Professor. So thank you, sir, for addressing these questions in quite detail. So with your permission, now we would like to conclude the session.
Absolutely. Thanks for your questions, everyone.
Yeah,
Very
thank
good.
you, sir. So on behalf of Bhaktivedanta Institute, I would like to thank for sharing all your insights in the lecture. And I extend our sincere thanks for everything, sir. Thank you.
A pleasure. Thanks, everyone.
So now moving forward with today's program, our next speaker is Sri Vasudeva, sir, President Bhaktivedanta Institute and alumnus of IIT Kanpur. He will be speaking on a very interesting topic. As you can see on the screen, does universe have a purpose? So before that, again, I would like to ask all the participants here to please scan the QR code displayed on the screen, and also the link has been shared in the chat box, so please do submit your questions to our speaker. So just let me give a brief introduction of our speaker today. Sri Vasudeva Rao obtained his MTech in computer science in 1998 from IIT Kanpur, India. After a brief tenure of working as a software professional, he decided to significantly contribute for the cause of humanity under the able leadership and vision of Dr. T.D. Singh, the founder director of Bhaktivedanta Institute. Presently, he is the president of Bhaktivedanta Institute, and for the past 25 years, he has been instrumental in actively fostering dialogue on foundational questions in science. He is also the editor of Bhaktivedanta Institute reputed annual journal Savijanam and travels widely across India and abroad. His deep interest in the foundations of mathematics, fundamentals of computer science and logic, and its relation to nature of reality, as well as ancient Indian texts, led him to interact and meet renowned scholars worldwide. So with this brief introduction, now I'd like to invite Sri Vasudeva Raoji. Sir, please.
Okay, are you able to hear me?
Yes, yes.
Let me share my presentation.
Yeah, it is visible, sir.
It is visible? Okay. Just a minute. Okay, thank you, Roshan, for that wonderful introduction, and thanks also to my previous speaker, Luke. It was very wonderful talk, and it will help a great length to my talk because I'm not going to cover too many details of the fine tuning, which I'm going to also use. And the audience who are posing wonderful questions and participating in this lecture series consistently. Today is fifth day, and online event is not easy to participate. So a big thank you to all the audience who are joining this event. So my topic is, does the universe have a purpose? So from a scientific point of view, it is not a question that has been settled, but this presentation is a journey that such a question to entertain an answer, what would be necessary and sufficient conditions. So that makes the first part of my presentation. So where we present some necessary conditions for a purposeful universe and some sufficient conditions for the purposeful universe to be considered as a scientific hypothesis. And in part 2, we will present an Indian traditional model of cosmology and consciousness to draw inspirations for modern cosmology research. So part 1. So necessary and sufficient conditions for the purpose. So this will be a comparatively smaller section, and I will be presenting in a summary of the points I would like to make, not in too much technical details, mainly due to the time limitations, that how much time I could dedicate and my own expertise. But this question is very much in my thoughts, so it's an humble attempt to bring to the attention of all of you. So the purpose is classically related to teleology, but it has changed a lot with the scientific advancement. In classical teleology, explanation of phenomena by the final purpose or goal they serve was sufficient. This was a central tenet of Aristotelian physics. But after the scientific revolution, teleology was largely expunged from physics in favor of strict, efficient, and material causation, discarding final causes. And then a concept called teleomy emerged, a modern distinction referring to the appearance of purposefulness that results from unguided mechanistic processes rather than the purpose in the very beginning. So the goal is to examine whether the universe exhibits genuine cosmic teleology rather than mere teleonomy. So in this process, the epistemological considerations are very at the center of the scientific method. It is very much influenced, today's scientific thinking is influenced by the falsifiability proposed by Karl Popper. The criteria is that a theory is only scientific if it belongs to a logical structure capable of describing an empirical observation that contradicts it. He also proposes conjectures and refutations. Scientists should boldly propose theories and subject them to serve critical testing. Theories that survive rigorous attempts to falsify them are said to be corroborated, not confirmed. So applying epistemology to our purpose quest, a scientific hypothesis of universal purpose cannot simply rationalize existing data. It must theoretically prohibit certain observations and also make formal predictions. Empirical science traditionally explains the mechanics of physical phenomena. But explaining why the fundamental constants of nature possess their specific numerical values was famously described by Richard Feynman as one of the greatest damn mysteries in physics. When fundamental parameters exhibit extreme non-random optimization, investigating the causal origin, why becomes a valid, necessary scientific endeavor. Logic of purpose inference. Our inference has to be best explanation. Inference to the best explanation. Teleological hypothesis must be assessed against competing theories, chance or physical necessity, based on explanatory power, scope, and causal adequacy. Scientific explanations require premises that contain universal laws and are known to be true. Scientific practice generally restricts explanations to natural phenomena, forcing teleological arguments to rely on intrinsic natural laws rather than supernatural intervention. So the necessary conditions for purpose hypothesis, conditions that must be present to legitimately entertain the hypothesis of a purpose of the universe. Their absence would falsify the claim. Number one, the presence of specified highly improbable complexity. And two, theories must stay within standard causal frameworks and yield testable experimental predictions. Three, the rigorous statistical or mathematical exhaustion of unguided mechanistic alternatives. So if these conditions are met, we say that necessary conditions are satisfied. So we take the specified complexity. The universe architecture must exhibit highly improbable configurations tailored strictly to an independently identifiable function. For example, capacity to support observers. Just as DNA functions like a software program containing specified information for life, fundamental physics must exhibit specific informational pathways to indicate purpose. The cosmic fine-tuning problem is one of the areas which can bring the necessary conditions. So, physicist Paul Davies, in his book Cosmic Jackpot, he raised this question: why is the universe just right for life? The observation that roughly 25 fundamental constants exist within infinitesimally narrow parameters. If these values deviated by even a fraction of a percent, the universe would fail to form stars, complex chemistry, macroscopic structures, or life. The purpose implication, the extreme statistical improbability of these conditions implies that the universe is strongly biased against being an unguided accident. The multiverse hypothesis is an alternative provided to avoid the implication of purpose. The multiverse proposes an infinite ensemble of parallel universe with randomly varying physical laws. I think this we have heard from other presentations also, but for the continuity of this talk, I will present here. Under the anthropic principle, it is trivial necessity that we observe a life-permitting universe, as observers cannot exist in hostile conditions. The scientific critique is that the multiverse invokes an overburdens of unobservable entities, requires speculative physics, and is widely criticized for lacking strict falsifiability. Then there are Bayesian consideration, like in one of the necessary conditions is to exhaust the unguided mechanistic alternatives, mathematical exhaustion. There is this paper on Bayesian considerations on the multiverse explanation of cosmic fine-tuning. In this, the two hypotheses that the universe is purposeful or came by chance, the multiverse. The two hypotheses. The likelihood ratio is measured using Bayes considerations. I'm not presenting the technical details here. Those who are interested, they can go to this paper. But the summary is that the overall result is that because multiverse hypotheses do not predict the fine-tuning for this universe any better than a single universe hypothesis, the multiverse hypothesis fail as explanations for cosmic fine-tuning. Conversely, the fine-tuning data does not support the multiverse hypothesis, which means that we can continue with the single universe hypothesis. Also, the argument also falls under inverse Gambler's fallacy. A major critique of the multiverse hypothesis is that it commits the inverse Gambler's fallacy. It is logically fallacious to infer the existence of multiple unobserved previous trials simply because an unlikely outcome is observed in the present single trial. The probability of this universe being life permitting by chance is not increased by the existence of other universes because each random event is independent. So this universe probabilistic approach is that because the multiverse fails to increase the predictive probability of our specific data, the fine-tuning data does not actively support the multiverse. And the paradoxical result would be that if the fine-tuning of our universe just happened by chance, but are surprisingly perfect for life, then this suggests purpose, not chance. The presence of fine-tuning provides mathematical evidence favoring the single purposeful universe hypothesis over the multiverse. Then there are also other theories like cosmological natural selection proposed by Simlon. It's called Simlon's theory. A teleonomic attempt to explain fine-tuning without a designer or standard multiverse. The universes reproduce via singularities of black holes, inheriting constants with slight random mutations. It also makes falsifiable predictions over generations. The typical universe will naturally optimize its fundamental parameters to maximize black hole production. But it is not the case in our universe, as refuted by Leonard Susskind. So basically, it is like biological natural selection, where the universe reproduces baby universes through black holes, and it adjusts its universal constants to maximize the black holes. It also suggests that an upper limit on neutron star mass, it is also challenged by observations of stars exceeding 2 solar masses. CNS merely shift the mystery of purpose up one level, a fine-tuned meta-law implying an intelligent cause required to set the evolutionary parameters initially. So therefore, our problem is not solved. Further, we can see from our Professor George F.R. Ellis, in one of the interviews with Dr. T.D. Singh, it is published in our Savigraman journal, I do not see any serious difference in the faith you need to believe in a multiverse and the faith you need to believe in a God who creates it all. Conclusion. The necessary conditions for concluding scientifically that the universe possesses a purpose have arguably already been met in several prominent areas of physics. But it is a contentious point, but we can assume or we can take position based on the data. Though there are opposite views and papers refuting, but this is the direction which we can proceed. The universe exhibits extreme specified complexity, most notably in the precise fine-tuning of fundamental constants required for life. Unguided explanations for this complexity, such as multiverse hypothesis, suffer from profound epistemic and probabilistic deficits including unfalsifiability and the inverse gambler's fallacy. Furthermore, teleonomic models like cosmological natural selection fail to escape the necessity of fine-tuning due to infinite regress of the meta-law dilemma. Additionally, reductionist materialistic frameworks have proven fundamentally inadequate in explaining the emergence of consciousness, cognition, and the qualitative nature of subjective experience, pointing toward the necessity of intrinsic teleological laws. But these necessary conditions are not sufficient enough to make a strong case for the scientific community. So we look for some sufficient conditions for the purpose hypothesis. Conditions that, if empirically observed and mathematically validated, would reasonably compel the scientific community to consider universal purpose. Requirements: direct, unambiguous evidence of intentionality encoded into fundamental laws, bypassing teleonomic explanations entirely. There are three pathways for this sufficient conditions. One is information theory artifacts, goal-directedness metrics, and directional complexity laws. An artifactual signature. The most direct proof of purpose will be the discovery of an artifact inscribed into the fundamental constants or observable background of reality, like cosmic microwave background. The signature must defy unguided generative mechanisms, display statistical invariance, and be strictly observer independent. Such an artifact would require fine-tuning of the initial Lagrangian prior to the Big Bang, avoiding continuous supernatural intervention. Because the universe we see is, we don't see supernatural innovations in a scientific investigation. So this is one of the requirements. The cosmic microwave background as a universal medium is very interesting. It is like the universal billboard. The relic radiation from the Big Bang fills the observable universe, visible to all advanced technological civilizations. Causal disconnection. Different regions of the cosmic microwave background sky were causally disconnected at recombination. No evolved civilization could coordinate a message across it. It could only be imprinted by an entity present at the creation, entity or agency. So this argument can be further explored in this paper by Su and Z, in titled Message in the Sky. In the abstract of this paper is very interesting to note that they state, very surprising, our work does not support the intelligent design movement in any way whatsoever, but asks and attempts to answer the entirely scientific question of what the medium and message might be if there was actually a message. The medium for the message is unique. So they are asking this question with very caution that they are not supporting intelligent design. So this, we can see the situation in, if we to take position, one has to be very careful. There are strong prejudice in the scientific research directions as well. And then second sufficient condition could be measuring goal directedness, mathematically quantifying whether the macroscopic evolution of complex physical systems behaves intentionally. Following Daniel Dennett, attributing goals to a system is scientifically justified if doing so uniquely maximizes our ability to predict its behavior. This measuring goal directedness is inherited from artificial intelligence, inverse reinforcement learning, utilizing advanced causal models to test if physical state transitions are actively optimizing a hidden utility function. In AI, it is important to measure goal directedness because it is critical element of many concerns about the harm that could cause from AI. Because suppose if AI develops its own some goal without our notice, then it would be very difficult for us. So they devise a mechanism to find the goal directedness or goal directedness that develops in the AI systems, if it is in the right direction or not, or such a goal is developed. It is also of philosophical interest as goal directedness is key aspect of agency. So this is then measure to see if the AI systems they develop the aspects of an agency, of their own agency. This method is of great value if it can be applied for quantum mechanics and also our cosmology research, because it can be used in case of both, because it would imply a agency in case of cosmology, a cosmic agency, and in case of quantum mechanics, quantum phenomena, it could imply individual agency or universal agency also. So this method is given in this paper by this group, also from Google Mind, the people are involved. So if we find a way to apply this measure to the cosmos, the phenomena and how the laws are and the cosmos is developing, whether there is any underlying function that is being optimized. Very interesting aspect of this method is that we don't need to know the utility function that it is optimizing, but still it can indicate that the system is optimizing an underlying utility function. Sufficient condition 3, directional complexity. Traditional physics relies on second law of thermodynamics as the arrow of time, increasing entropy. The universal complexity law proposes a non-decreasing time asymmetrical general complexity potential omega for open non-equilibrium systems. The implication is that if physical laws mandate a continuous complexity flux greater than 0, then life is thermodynamically driven inevitably, not a statistical accident. So if the physical laws are mandating a continuous increase of complexity, then it could indicate a thermodynamical inevitability of life. This method can be further studied in this paper by Donglu Shi, appeared in Entropy, and is available at this website address. And further, the limits of mechanistic biology. Thomas Nagel's critique in Mind and Cosmos, philosopher Thomas Nagel argues that materialist neo-Darwinism fundamentally fails to explain the true nature of reality. It has 4 failures. 1, abiogenesis, how first living cell has been generated. Subjective consciousness, how the subjective consciousness arises. Rational abstract thought, how the abstract rational thought has evolved in the humans. And objective moral values. And the hard problem of consciousness, because physics cannot account for qualitative subjective experience, and unguided causal history is mathematically and philosophically incomplete. Nagel rejects traditional theism but posits naturalistic teleology, the existence of fundamental teleological laws intrinsic to the cosmos. The universe is not just pushed by random physical mutations from the past, but is actively pulled toward a telos of cognition and value in the future. Conclusions. The scientific enterprise has not yet satisfied the sufficient conditions required to definitely and empirically conclude that the universe is purposeful. Achieving this momentous paradigm shift requires the successful execution of specific observational and theoretical objectives. Detection of an artifactual signature, quantification of intent using goal directedness, and validation of directional complexity. Further, if one or more of the sufficient conditions are realized, epistemological boundaries can be re-examined to facilitate the possibility of purpose in the universe, which is immanent as well as transcendent to the physical universe. This will also help ongoing consciousness research. So now we'll go to the part 2. This is inspirations from an Indian traditional model of cosmology and consciousness for modern cosmology research. For those who are interested to know the cosmology in Indian tradition, one of the models is Sankhya, and it is the process of how universe comes into existence is very given in very details in the Srimad Bhagavatam, in the different cantos I have given here. It describes how the elements comes into existence, how the consciousness comes into existence, at what point the consciousness is introduced, the time is introduced, and so in this way very interesting. And also in Bhagavad Gita there are certain portions in Bhagavad Gita which talk about the universe, and these books can be found at this website vedabase.io, and those who are interested, they can go further. Here I would like to present a quick glimpse into it. And the details will, I think, probably come tomorrow in the talks that are coming tomorrow in Indian knowledge systems. So in the Gita, Lord says that Mahat Brahma is my energy or source that generates everything. I am impregnated with souls, therefore I am the seed-giving father. Then in Srimad Bhagavatam, the process of creation is given. There are 3 things called Pradhana, Prakriti and Mahatattva. Pradhana is unmanifested and undifferentiated sum of all material elements. So it includes 3 modes that are in balance or in equilibrium. So this is like unmanifested potential energy form of material cosmos or material existence, which is there in the initial form. When this pradhan is agitated by time factor, time energy of the Lord, and the glance of the Lord with the souls, the manifested and undifferentiated sum of all material elements is possible. So the unmanifested energy comes into the form of manifested energy, and by agitation of the modes of nature, the 3 modes go out of the equilibrium, sattva, raja, tama, and then manifested and differentiated sum of all material elements becomes possible. Implications or inspirations for Big Bang. Universe was said to be emerged out of pores of body of Mahavishnu. So therefore, Big Bang-like process not ruled out as universe manifests from the Pradhan, which is the unmanifested form. However, it is mediated through consciousness, a glance of Mahavishnu. Dr. T.D. Singh called it big vision. Both expansion and contraction of universe are possible because in the process of creation, the universe comes into existence from unmanifested potential state of material energy into diversified universe, and after the end of the age of the universe, it is again annihilated back into the same way. Interestingly, the age of universe is comparable to the scientific age of universe, and even older than the scientific age of universe. Observers are fundamental entities injected into the cosmos during initial phases. So this is very interesting. In the Indian cosmological model, they don't simply say that God created, but they give very detailed process that at what point the material process of creation, but they are fundamental, but are injected into the cosmos during initial phases and occupy the different species when they are available. But where do they exist before the universe? This is a question that we will explain in the further sections. There are 24 elements, 5 gross elements, 5 subtle elements, 5 working senses, 5 sense organs, and 4 internal subtle elements. So if we simplify it, this is simplified in Bhagavad Gita, we see this, at the bottom, we will see Panch Mahabhutas, earth, water, fire, air, ether. From them the senses are formed. Above the senses there is mind, man. Above the mind there is buddhi, intelligence, and above intelligence there is ahankar, ego, and above it there is the soul or soul possessing consciousness. And in this hierarchy, God actually is in the top of the hierarchy, who even mediates the three modes of nature for the manifestation of the universe and sustenance of the universe and dissolution of the universe. And also he gives guidance and company to the spirit soul in the heart. So we take one of the fundamental particles, that is among these. We take inspiration from the physics that the fundamental force in physics, they're always associated with the fundamental particle. But there is a possibility that there may be forces other than the four forces known in science. It is unreasonable to think that we already know enough about the natural world to be confident about the totality of forces. Michael Pollan's this remark is very important for us, because there is always friction to embrace new fundamental shift in the science. The recognition of certain basic impossibilities has laid foundations of some major principles of physics and chemistry. Similarly, recognition of the impossibility of understanding living things in terms of physics and chemistry, far from setting limits to our understanding of life, will guide it in the right direction. Such a demonstration would help to draw a truer image of life and man than that given by the present concepts of biology. So he's encouraging us to not be afraid to embrace fundamental changes, and that will only help science and also our understanding of life. So in the past, we see these impossibilities and the principles they have given rise to. So similarly, impossibility of reduction of life or consciousness to chemistry could give up new principles. One of the principles from Indian knowledge systems about the life is that a pleasure principle, that every person is endeavoring to be happy, every living being is endeavoring to be happy. Even an ant wants to have lasting happiness. Happiness instinct is more fundamental than the survival instinct. So therefore, sometimes we see that some living entities even terminate themselves. So happiness, therefore consciousness, is a fundamental force in the living systems. Therefore, there must be a fundamental particle that is responsible for consciousness. In Vedic tradition, it is called soul or Atma. We can think about it as a quantum particle of consciousness. We say quantum because it has definite quantity, particle because it has definite size, and it is also transcendental to this space because it is not made of the elements of this space and time. And it has the properties of being eternity, conscious, being happy. So because happiness is a fundamental property of the soul, or fundamentally preferable state, so therefore it shows up in the life. Consciousness to soul could be similar to what charge is to electron. If we sometimes difficult to understand what is consciousness and soul. That means consciousness is always associated with underlying soul, just like negative charge is always accompanied by an underlying electron. So if you see the ontology in this model, the fundamental particles which we are discussing in physics, they mostly fall in the 5 gross elements area, because these 5 gross elements also include sky, which could indicate the space. That means there are many more fundamental particles to be found in the realm of mind, intelligence, ego. Teleology of Sankhya, understanding the elements by their purpose. So, the elements mentioned in the Sankhya like mana, buddhi, and ahankar, mind, intelligence, and ego, these could be understood by their purpose or function rather than their physical properties. So from there, if we understand them, that may help us in devising our physics, because these elements in the level of mind, intelligence, ego, they are all still material, because the initial pradhan, from initial pradhan of unmanifested potential energy, all these have manifested except the soul which has been injected from outside. So therefore, in principle, they're all the same, of the same material nature, but in different subtleties, in varying degrees of subtleties. So by careful experiments or thought experiments, we could either detect, we can devise experiments to detect, or at least we can infer the existence of those entities, because they are present in our cells, in our psychological process. So we try to explain this purpose or function of these elements using a video game example, because the same elements come into picture when we play a video game. This is a game. I think you have to must know some base of a boy is trying to run away from the police. He's chasing with the dogs, and on the way he's trying to collect coins and maximize. So I go a little faster because our time is coming to close. When we play a video game, the first thing we have to do in order to play a game is that we have to identify with the character of the boy. Then only we can play this game. Otherwise, very soon we will not be interested. So, in the process of identification, the ahankara, the purpose or the function of the ahankara is facilitating our intention to identify with something else, facilitating the identity change. So false, the name is also given ahankar. Ahankar means, aham means I. So therefore, I-ness, or the name is also given like that in the Sankhya, ahankara, that is responsible for identity change, or that which mediates our identity change. Why do we change our identity? Again, it is because of happiness. Though we have so much identity battles, but if we are presented with happiness, we are ready to change our identity. Means we can sacrifice our identity, present identity, in lieu of the happiness, and embrace another identity. So the soul accepts the body to change identity so that it can be happy. So the purpose of biodiversity is the happiness, and to facilitate the consciousness of the living being or soul in different living species, because the living entities are souls who have different levels of consciousness. They would like to live life in different way. So some would like to fly, some would like to swim, some would like to be vegetarian, some would like to be non-vegetarian, some would like to be peaceful, some would like to be violent, some would like to help others. So in this way, in different varieties of consciousness are facilitated through this biodiversity. The purpose of diversity is to facilitate the conscious levels of living entities and facilitate their happiness. So in the Padma Purana, it even gives the list of the different forms, biodiversity in different forms. The change of identity we not only experience while we play a video game, we also actually experience when we dream. When we dream, actually, we accept a dream body temporarily, and we experience the dream world. Buddhi is an intelligent module. It generates algorithms for the things required, and it also stores the algorithms or results of executing algorithms earlier. So that when we change from one body to another, we don't need to carry the local algorithms. For example, how to run in a body of a tiger. So when the tiger is baby, it doesn't know how to walk, so slowly it learns, and its intelligence gets fixed at various levels of motors and how to move, how to walk, all these things. Stores, and it also evaluates pros and cons of our intention, and also it gives means to achieve things. In the driving example, in Buddhi, we carefully calculate every move when we learn driving. But when we are experienced in driving, we do not calculate much. Buddhi is tuned. A first-time smoker tend to evaluate the consequences. Habitual smoker hardly cares for consequences, even if warned on the cigarette packet itself. Buddhi is tuned wrongly for momentary happiness. It is called polluted intelligence, in the sense that once few times you evaluate your preferences, the Buddhi element in our subtle exist in us, that gets tuned to what we prefer. So therefore, it doesn't interfere in between to evaluate, and so therefore the Buddhi is said to be wrongly tuned. Then the mind. What is the function of the mind? The function of the mind is to polarize our thinking, because thinking is an aspect of consciousness. Thinking, feeling, willing, they're all functions of consciousness. The function of the mind is to filter out. Polarize means to filter out the thoughts from other identities, so that we can happily enjoy the present identity. Because when we play the video game, we need to be continuously in that identity if you want to enjoy the game. Suppose if our friend sitting next to us, it disturbs us, we don't like it, because that disturbs our enjoying the game. So if you want to enjoy the video game, it is necessary that we remain in that identity until we play the game. So therefore, mind is so tuned that whatever identity we are presently situated, the mind brings thoughts in that direction, in that identity. So it is like wearing a red spectacle. If you wear the red spectacle, then we will see everything as red, because it is not that we cannot see every other color, but because the spectacle that we have taken, put on our eyes, it is filtering it out other light. Similarly, like a horse, they are put blind so that they can only see straight. So therefore, mind does the same thing. It keeps our thoughts channelized to our present identity. So for that, our mind, if we are idle, then it will remind you your activities, past activities, or future possibilities of this life, this present life. So engage your mind, otherwise mind will engage you. So because mind wants to keep you engaged in this, continue in this identity, it will randomly give thoughts, good or bad, if we keep it idle. So therefore, if we engage it, it will be in the right direction. But if we leave it idle, then it will be random or unpredictable. So identity is the basis of our mind polarization. That is how the purpose of the mind is, so that we can be happy. We don't remember about the past life. We don't need to worry about what has happened before, but we can make a fresh start and try again in this life what we want to be. So from this example of video game, we can make some inferences about time and space of this universe based on our Vedic Srimad Bhagavatam cosmology. Either just like this game is actually simulated in the small portion of the screen on this computer, right? In this we see trains, we see boy, everything in this small space. Similarly, this universe is simulated in a larger space. Just like this space is a very small portion of our present space. Similarly, this physical universe, the physical existence, actually not just one universe, there are many universes. This actually occupies a small space in the absolute space and time. So, but this simulation is not like a very virtual, and not necessarily has to be digital. It could be digital or it could be analog. But as long as you provide me a body where I could interact with it and experience the spectrum of conscious experiences, I will occupy that body. So therefore, whether it is analogous or digital, we don't know, but it could be we can think in the terms of simulation, not exactly like a computer simulation, but something that is realized in this space. And it is said that from absolute space and the spiritual realm, this realm where the material universes are created, it looks like a cloud. Similarly, the computer has its own time or clock, because each and every instruction is mediated through its own time cycle, memory fetching and all this data, memory, writing, or arithmetic calculations. They're all sequenced using an internal clock. If we reduce the speed of the clock, the computations, they will go slow. And depending on how we program the display, it can also go slow. So it indicates that just like the computer has its own time derived from this time, similarly, the time which we have here is actually existing in the absolute time, and it is derived from there. And so there is an absolute time and space before the creation of the material universes.
Excuse me, sir. Sir, you have 2 minutes left.
Okay, let me try. So I skip this. Tomorrow you will learn something about the relativity. Okay, so implications for consciousness. Since it is possible to experience the game world without the player being part of the space of the game space, it is possible for the conscious observer to experience this physical world without physically being part of the space of the manifest physical reality. So when we play the game, we are actually not inside the space of the game. We are actually sitting before the computer, but we are able to experience it, provided if we are given an medium or a channel where we can experience or associate with it. So similarly, the soul can experience this physical universe, visible physical universe, without being physically part of this manifest physical reality. Means if some part of the physical reality is unmanifest, it could still be part of that. Unmanifest in the sense which is not accessible to us right now. Conscious observer could be transcendental to visible space, time. Conscious observer could be transcendental to the visible space, time. So this is called transcendence, means just like we are transcendental to the video game, it is possible that the consciousness is transcendental to the physical world, though still interacting with it. So in such case, the methodological naturalism would be difficult to find it or find it in the lab. We can infer through different means, but maybe a little difficult. So physical world is a bio-cosmological simulation, not in the way a computer is simulated, but the real matter is used to simulate it. So the purpose of the universe, according to the Sankhya or Vedic model, is to give a habitable place for the observers who like material atmosphere, and to facilitate the material desires of such observers, and to allow attempts of such observers to be happy, and to purify their consciousness by pravritti and the nivritti of material desires. So pravritti means facilitating the desires, and then when they are little bit bored, they want to find something higher. So then they look for some higher spiritual engagement rather than just material indulgence. So the universe is designed to facilitate both, and this is the purpose of the universe. So we need both scientific temper plus ideas from traditional wisdom, because both are useful and important. As Sir Roger Penrose says, perhaps we may never be able to understand the ultimate reality through rigorous scientific approach alone. So therefore, a scientific temper and traditional wisdom ideas, when we put them together and use scientific temper to rationality to understand them and not be fanatic, that will be the best combination. And as my colleague Varun says, can we really afford to live in a universe without purpose and a life without meaning? Thank you very much for your attention.
Yeah.
Hello.
Hello. Yeah, thank you, sir, for your very insightful lecture. And I would like to express my sincere gratitude to you for sharing such profound insights regarding the purpose of the universe and briefly giving the overview from Indian knowledge system. So, can you, some screen is coming. Yeah.
My screen is stopped? Not yet.
Yes, yes, it is
Stop.
stopped.
Stop.
So I will again request all our participants to please scan the QR code shown on the screen, and please submit your question using the chat link in the chat box also. So we have got some few questions. So let me begin with Professor Lewis from York University. Thank you for this very interesting presentation. If it turns out that the age of the universe is much larger than estimated by current cosmological models, this would provide much more time for physical and conscious structures to fully develop. How would this affect our understanding of the purpose of the universe?
Well, the purpose of the universe from a point of view of Sankhya, it remains the same. But how it would actually affect how the universe is developing, that is, I think, your area very much. But the purpose remains the same, whether it is, maybe it is because we may further, the two values may coincide when the more we go further. That is one possibility. And another possibility is that there may be discrepancy in calculating our Vedic time, also possible. There is some discrepancy in calculating the scientific age of the universe is also possible, but it is of the order of 10 to the power of 4 times bigger, as it is mentioned. The purpose still remains the same.
Yeah, next question, please. Yeah, this is question by Pradeep Kumar, Kendriya Vidyalaya Sangathan. Thank you for the lecture. If the spiriton is eternal and pure consciousness, while the ego is a temporary material construct, what is the exact glue or functional mechanism that allows a non-material entity to become entangled with the material one?
Can you keep the question a little bit time? So, one thing we need to understand is ego is not just a temporary material construct. It is ego identity is already existing with the soul. So ego is not creating a sense of identity. it is not giving sense of identity to the soul. It is only helping to mediate it. So that means when you are situated in your original identity of who you are, that is actually called self-realization. And functional mechanism, how it glue exactly does is not given in the books of the tradition, and but we can understand them only in a functional way right now, and maybe in future in scientific advancement and applying it to our psychological processes, something better may come out in future.
Yeah, thank you, sir. Third question, please. This is question by Ritvik. Can you highlight about the capacity to support observers, which you shown in one of the slides?
It's same like our previous speaker also has spoken on this fine-tuning of the universe, which appears to be finally destined to support us, the conscious living beings or life. So that is the meaning of it. How come that the constants are so fixed that the intelligent life comes? If it is just only a chance, then the appearance of observers like us makes it less improbable that the fine-tuning of the universe is by chance.
Yeah, thank you, sir. We will take one more question is there. So this is question by Pragya. According to Bhagavad Gita and broader Hindu cosmology, there are multiple universes, each governed by its own Brahma and sustained by Vishnu. Given this idea, could it possible that the Atman is not limited to a single universe, but exists simultaneously across multiple universes? And if so, could our dreams be a form of connection or reflection of experiences from these parallel existences? While there may be no physical evidence for this, is such a possibility conceptually or physically valid, philosophically valid?
Yes, because the experiencer, so first of all, the soul exists only in one of the universes, not simultaneously in two different universes. But depending on our destiny, we could be transported to another universe also in another cycle, or even in this cycle, that I'm not sure. But it is very much possible that we could be part of another universe in the previous existences. And since the experiencer is the same here and there, and we do remember some of the, it's possible that sometimes we remember our past experience in the parallel universes. That possibility exists. Only if the Lord who is in the heart is mentioned, that our memory and remembrance and forgetfulness, if you see the Gita, our remembrance and forgetfulness are mediated by the super soul. So therefore, at present we were made to forget our previous existences for our own good, because suppose if you remember your past life parents, then the dilemma will arise, would you like to go to them or would you like to stay with the present parents? So such complications will arise. So to make our life more simple and happy, the Lord has given us forgetfulness of certain things, not only of past life, but also present life also. Certain things, if you don't forget, we cannot be happy. Sometimes we try to forget unwanted things, but it's not in our hands entirely. There is also a factor of super soul who mediates it. So therefore, the dreams could be one of the possibilities of experiencing our past experiences. For example, you want to be a king or something which you are not able to be, but you have previous experience of being a king. So therefore, Lord could bring that previous experience in the form of dream, so that at least while sleeping in the night, we are happy temporarily. So that possibility exists.
Yeah, thank you very much, sir, for this answer. So we will take a last question here. This is question by Naveen, Naveen from Aizer, Kolkata. Science reduces our existence to temporary, unguided chemical reactions governed by physical laws, while Vedic philosophy elevates us to eternal Atman, participating in a grand cosmic order. If both of these paradigms are ultimately just human construct, one designed to locally organize and manipulate the
Not
material,
clear.
and the other invented to psychologically cope with terrifying prospect of an endless universe. On what grounds should we accept either as the absolute truth? Furthermore, when trying to reconcile the tangible reality of matter with the profound human need for purpose, why should we trust any synthesized perspective, including yours, to tell us what is actually real? So there are two questions, I think.
Okay, ultimately, it is individual preference. See, our theories, what we believe is also governed by what we want to believe. This is also because our theories, we postulate, there is an element of our preference, what we want to be. So therefore, these different paradigms are given, but ultimately it is up to the individual to evaluate. And there is no absolute proof of either. So therefore, you have to use your own evaluation, your own personal experience, your own psychological process, and your own preference about meaning and purpose in life. Some people don't care if there is a meaning in the life, just live what we like. So this is also our preference. There is a preference is there. But if one is interested, there are different paradigms are presented, and one has to evaluate with the open-mindedness that both are not contradicting, but appear to be contradicting at certain points. But if it is a single reality, there may be possibility of synthesis. So because the physical process or the physical laws are not able to fully satisfactorily satisfy our quest to understand our own selves, one is to wait forever that science may solve this, or another is that since our life is short, also evaluate other process. And when you say evaluating the other process, it is not just a theoretical evaluation. One also need to do certain experiments in this line also, just like we do experiments in physics. And there are people who have followed this process and expressed certain spiritual results in the past. So we can also test it and see if those results are coming, if you are interested to investigate in this direction. But otherwise, only on the theoretical level, it is up to individual preference. And if one is open, one may have possibility of a synthesis or understanding the domains where they apply. For example, the moral law or the set consciousness. One thing is that they are material. One thing is to decide that they are material, physical laws, and in future we will find out. Another is that there may be fundamental, another particle like mentioned in the scripture, so that we can take them as a kind of hypothesis or hints, not as absolute in the beginning, but as you experiment yourself, open mind, without prejudice, then definitely we will find an answer.
Yeah, thank you, sir. Thank you very much for addressing these questions. We still have more questions, but we will conclude with your kind permission. So on
Thank you very much, Roshan, and all the participants for joining this series and this talk. Namaste.
Yeah, thank you, sir. I hope it has given all the audience a different perspective regarding our universe. So thank you. So our final speaker has already joined, and it's Professor Frank J. Tipler, Professor of Mathematics at Tulane University, USA. So Professor Tulane will be speaking on a very interesting topic: the universe, its beginning, its end, and the role of humanity in universal history. So before that, I would just like to announce that again, that please scan the QR code to submit questions to Professor. And also the link has been shared in the chat box. So please click on the link to submit your question anytime during or after the session. So just a brief introduction of Professor Tipler. Frank J. Tipler is a professor of mathematics and physics at Tulane University and a pioneering figure in the study of global general relativity. He is the co-author, along with John Barrow, of the definite scientific treatise, The Anthropic Cosmological Principle, which rigorously investigates the necessary physical constraint for the emergence of intelligent life. His expertise in the causal structure of space-time led to the discovery of Tipler cylinder, a celebrated exact solution to Einstein field equations that theoretically permits the existence of closed time-like curves, demonstrating that the laws of physics do not strictly forbid time travel. Renowned for pushing the logical limits of physical law, Tipler formulated the omega point theory, a provocative cosmological model that synthesizes thermodynamics, information theory, astrology. He argues that the known laws of physics requires the universe to evolve towards a state of infinite computational capacity, enabling the indefinite continuation of intelligence and the potential simulation of all past physical states. This work, often described as the physics of immortality, represents one of the most daring and mathematically rigorous attempts to deduce the ultimate destiny of consciousness from the fundamental axioms of the universe. So with this brief introduction, I would like to kindly invite Professor Frank J. Tipler to deliver his talk. Welcome, sir.
I'll be happy to do so. I hope you can hear me.
Yes, yes.
Excellent. Then if you'll put the first slide up.
Yes, sir. So just wait a minute. We are, yes, sir. So there is some technical issues happening. Just wait a bit. We are
Inevitably technical issues.
Yeah.
Here we are. Yay. Okay. Oops.
Sorry for the delay, sir.
No problem. I'm used to these technical issues. Okay. What about the next slide?
Yeah.
Okay, what I'm going to talk about really fits under the category of the final anthropic principle, and it fits in with what the previous speaker said. In the original formulation, it says, in any universe, intelligent life must come into existence and persist until the very end of time. I will reformulate it today in much more abstract terms. A universal computer, a computer, in other words, equivalent to a universal Turing machine, will, in the course of future history, be consulted. What I will shortly do is show that the laws of physics imply that such a computer will, in fact, be constructed. But why worry about the far future? We can't observe it. The reason in physics to worry about it is because requiring the consistency of the laws of physics in the far future constrain the universe now, which we can observe. Next slide, please. Historical fact. Physicists, even the great ones, typically reject the laws of physics when the laws of physics imply something they happen not to like. Example one, Einstein famously introduced the cosmological constant, the worst mistake of my life, he called it, to eliminate what his own equations implied, namely that the universe had to be expanding. Now, that discovery, the fact that the universe is expanding, was the greatest cosmological discovery in the first half of the 20th century. Second example, Steven Weinberg, in his A Historical Diversion chapter of his book, The First 3 Minutes, wrote that he personally, Nobel Prize winning great physicist, rejected the laws of physics because they implied the existence of an early universe filled with a cosmic background radiation. The CBR, of course, was the second greatest cosmological discovery in the 20th century, the greatest cosmological discovery in the second half of the 20th century. Next slide. Next slide. People, I need the next slide. Okay, the next slide, if you can get it. The great cosmologists, there are many here today, are repeating the mistake. They're rejecting the laws of physics. What are the laws of physics? My colleagues here, and again, they're great cosmologists all rejecting. First, the second law of thermodynamics. Second, quantum mechanics, specifically unitarity, the Bekenstein bound, otherwise known as the uncertainty principle, and wave packet spreading. They're also ignoring the standard model of particle physics, specifically the Higgs and SU2 left fields, general relativity, which implies the universe began in a singularity, and also spin 2 quantum gravity, otherwise known as the Feynman-Weinberg-DeWitt-Wheeler theory of quantum gravity, which also implies an initial singularity. Next slide. These laws of physics solve most, if not all, cosmological problems. Which problems? First, why is the universe homogeneous and isotropic? This follows, as I'll show, from the second law of thermodynamics and the Bekenstein bound, no fine-tuning of the inflaton field, or no inflaton field at all needed. Why is the universe flat? That comes from standard quantum gravity and old familiar wave packet spreading. Why do ultra-high energy cosmic rays exist? Now, these are extremely high energy protons coming in from intergalactic space, and they should not exist according to standard cosmological theory. But we've seen them for 60 years. Many groups have seen them. They are a real phenomena. Next, why is there only matter and no antimatter? Let's go back. Why did WMAP and the Planck observatories observe the Sanyaev-Zeldovich effect to be too low? It's the SU2 field. The ultra-high energy cosmic rays, it's the SU2 field. Why is there matter, only matter, and no antimatter? It's the SU2 field. What is the dark matter? And what is the dark energy? Dark matter, that's answered by the standard model Higgs field. Dark energy, it's the standard model vacuum. Next slide. Let's see how this works. First of all, we need to study what physics tells us about the far future. And we all know Hawking showed black hole evaporates. Now, he also showed that were a black hole to evaporate completely, the principle of unitarity would be violated. Now, black holes certainly exist. We've seen thousands of them. And were the universe to accelerate or even just expand forever, then all of these black holes we've seen would evaporate to completion, violating unitarity. But unitarity, which is a fundamental principle of quantum mechanics and implied by law of energy conservation, Susskind, University of Stanford University, showed that energy conservation violation by unitarity violation would amplify blowing up the planet Earth. Doesn't happen. Can't have unitarity violation. It can't be violated. So, conclusion, no black hole can evaporate to completion. According to general relativity, the only way this can happen is for the universe to come to an end before any black hole can completely evaporate. Again, according to general relativity, the only way the universe can come to an end is for the entire universe to end in a final singularity. Black hole singularities necessarily then are part of the final singularity. Okay, next slide. Now, Bekenstein showed that his bound implies that were there to be event horizons at the final singularity, the entropy of the universe would have to approach zero. But the second law of thermodynamics says the entropy of the universe cannot decrease, and the entropy of the universe today is currently far above zero. Thus, event horizons cannot exist. And this is a central statement of my omega point theory. Event horizons do not exist. That's why it's an omega point. It's a single point in the Penrose C-boundary construction. Now, a theorem of general relativity tells us further, this is the Sachs theorem, that if there were no event horizons, then the universe must be closed, mathematically, in mathematical language, spatially compact. Now, notice the important thing. The far future is now telling us what the universe must be like now. It has to be closed. Next slide. Now, let's consider what physics problems are actually solved in passing by having no event horizons. If there are no event horizons at all, in particular, there are no black hole event horizons, then of course information can get outside from the inside the black hole. Black hole information problem solved. Also, if there are no event horizons, then black hole firewall problem. That's a problem which people realized a few years ago that quantum field theory requires, if you have an event horizon just inside the black hole event horizon, quantum fields have to diverge in energy. That problem is solved. No event horizons. Now, remarkably, it's not generally realized that there are event horizons even in standard Minkowski space. But of course, they're not black hole event horizons, which come from trapped surfaces. And of course, there are no trapped surfaces in Minkowski space. Now, a careful analysis, which I've given in a paper, and I'll give it later if you want to read the details, these particular event horizons in Minkowski space cause a firewall problem, infinities, in standard quantum field theory, both those which can be renormalized away and those which call quantum field theory series, when you expanded a power series of scatter the S matrix in a power series involving the coupling constants, to be asymptotic rather than converge. These infinities also disappear if there are no event horizons. Next slide, please. Now, what was the initial state of the universe? Once again, the standard model of particle physics and the Bekenstein bound give us the answer. Remember, Bekenstein showed if you approach a singularity, if you have horizons, then the entropy has to go to zero. In the early universe, we will have horizons, not event horizons, they'll call particle horizons. Particle horizons just time refers to event horizons. As you're going into the initial singularity, therefore the entropy of the universe has to be zero. The temperature also has to be zero. Now, zero entropy, what does that mean? It means the universe was in a unique state. The standard model tells us what that unique state is. It has to be a perfectly isotropic and homogeneous three-sphere. Now, remember, all we can deduce from the future, spatially, universe has to be compact. But now, the Bekenstein bound applied to the early universe tells us that compact space has to be a three-sphere. Filled entirely with one field, and the standard model picks it out. It's a self-adjoint SU2 left field. Such a field in an expanding universe will generate only matter, not antimatter. How this works, how this particular field will generate only matter, I refer you to Steve Weinberg's beautiful book, Quantum Theory of Fields. Next slide. If an XU2 field survived to the present day, it would constitute the cosmic background radiation. Now, two observations suggest that the background radiation is, in fact, primarily an SU2 left field. Remember what L means. It means the field couples to only left-handed quarks and leptons. Relativistic free electrons in galaxy clusters, that's what we're doing when we're measuring the SZ, Sonyaev-Zeldovich effect. The background radiation particles are coming through galactic clusters and they're scattering off relativistic electrons in those clusters, and that gives rise to a temperature shift. That's the Sonyaev-Zeldovich effect. But if SU2 left is what is the primary makeup of the background radiation, these cosmic background particles would interact with only half of them, so the Sonyaev-Zeldovich effect would be half of what standard theory, assuming the CBR is all photons, would predict. And that is what W. Maup and Planck actually saw when they observed the background radiation, looking at the SZ effect. Next slide, please. Now, more details of how the known physics solves this. All right, now let's solve the problems. Let's think about this. Dark matter, if the standard model is correct, then the standard model has to tell us what the dark matter and the dark energy are. Why? Because the standard model purports to be a theory of all forces and all particles except for gravity. Well, if there's dark matter around, there is, and there is dark energy around, there is, then the standard model must account for it, and it does. Now, what does it say? It says that the dark matter has to be an oscillation of the Higgs field. We know that a Higgs field, a scalar field, which satisfying the same equations to first order as the standard model, Higgs field, would produce a background field that is has its pressure zero. In other words, it is cold, dark, because the Higgs field would interact weakly and gravitationally with other matter. So that's exactly what we have. Now, in the process of creating the particles in the universe, the method is tunneling of the standard model vacuum, and that will have a back reaction effect on the vacuum. And it's been known for decades that the vacuum energy density is exactly a cosmological constant. So the creation of matter changes the cosmological constant, the standard model cosmological constant, from its actual value of zero to slightly positive. So we get the dark energy too. Now, why is the universe near flat? It's observed to be within experimental observations. The actual explanation is wave packet spreading. There's a theorem that if the universe is classical now, which it obviously is on the large scale, then its wave function must have been a delta function at the initial singularity, which incidentally shows the initial singularity must exist. You don't need fine-tuning, because what happens if you have an initial delta function, wave packet spreading says it's going to explode outward, and each classical three-sphere universe then would be almost flat. You can look at the details in a paper, which I will reference in here we are, in my paper, Reports on Progress in Physics in 2005. Okay, now I've given some more details, particularly about the dark matter and the dark energy, in a more recent paper, the British Interplanetary Society Journal, in 2024, if you want the details of the mathematics. Next slide, please. Okay, let's now consider in more detail the ultra-high energy cosmic ray problem. All right, now what are they? They are protons with energies so large that they lose energy by pion creation whenever these protons clobber a CBR particle, whatever they are. Now, most of the cross-section for this particular process is due to a quark spin flip, which cannot occur if the background radiation is an SU2 left. Now, an ultra-high energy cosmic ray particle has a mean free path of only 3 megaparsecs, if the CBR is all photon, that's standard theory, but it has 450 megaparsecs, that's nearly half a gigaparsec, if the CBR is SU2 left. all the ultra-high-energy cosmic rays would be coming from the Andromeda galaxy if the CBR were all photons, and that's grossly inconsistent with observation. Quote a most recent example of an ultra-high-energy cosmic ray coming from apparently nowhere, the sun goddess particle, named after the Japanese sun goddess. It's coming from, this was reported in Science last year or so, coming from a void. There's nothing there. Now, my student, Daniel Piasecki, and I have been able to identify sources for all of the ultra-high-energy cosmic rays, assuming that the CBR is mainly SU2 left. People can't identify any sources for most of them if it's standard theory. The problem, ultra-high-energy cosmic rays, an anomaly for 60 years is now solved if the background radiation is SU2 left. Next slide, please. Now, let me emphasize, those who are ignorant of history are doomed to repeat it. Let me give you two examples from astronomy. John Couch Adams predicted the location of the planet Neptune long before Urban Le Verrier did, but Adams was unable to persuade any British observer to look for the planet. Now, historians have pointed out that he had telescopes in his possession which were perfectly capable of detecting Neptune. He should have looked for Neptune himself. Second example, Alpha and Herman predicted the background radiation in 1948, as we all know, but they were told by experts in microwave technology at Johns Hopkins Applied Physics Laboratory that it was impossible to find such an object. That's actually false. The Dickey interferometer, which had been made in the Second World War, could have detected it, couldn't detect it in Boston, but if you tossed it in the trunk of your car, it was a really small instrument, drove to the top of Pikes Peak where there was no water vapor to speak of, you could have easily seen the CBR. Conclusion, Alpha and Herman should have done the experiment themselves. I have determined that I am not going to repeat past errors, so I decided I would directly test for the SU2 left CBR myself. Next slide, please. I persuaded the IT billionaire Peter Thiel to fund my experiment to directly test for the SU2 left nature of the CBR. Now, the way the experiment works in outline is this. If the background is indeed SU2 left and not photon, it would interact only, as I've mentioned before, with only left-handed electrons in a dielectric. Now, left-handed here refers to helicity, not the same as spin at non-relativistic energies, only at relativistic energies, and needless to say, we don't have relativistic electrons in a dielectric. But even CBR passing through a dielectric would interact not with 100% of the particles, but greater than 1/2, but less than 1. And thus, this would change the index of refraction as measured by the instrument if the CBR were SU2 left. It would be less than the photon refractive index, which we can look up and measure. Okay, so here's the basic idea. Send the CBR to a Fabry-Perot interferometer. That means you're measuring power of the background radiation or whatever radiation comes through at different frequencies, and you compare the CBR with an all-photon signal. Now, here are the results using the silicon. We use silicon as our dielectric because it has very little emissivity, so little background radiation coming from it, and a very high refractive index. Other materials can be used. Silicon is it's truth be known, it's the cheapest one we can find. We virtually got it for free. Next slide. Okay, let me show you the experimental apparatus. Most of this structure is just a screen to prevent background from the ground from coming in. And what you'll see in the very center of this picture is a little white circle. That's a plate holder for the silicon plates. Next slide. Now here's a more detail of the actual interferometer. You see the microwave horn, and you also see, this is at night because we do our observing at night, you also see the silicon plates in the holder right above the horn. Okay, that's the apparatus. Now, let's see what we should see. Next slide, please. Now, first of all, we made sure that we would have exactly what we should have if all photons were coming in. Now, the details of the interferometer, how the machine actually reacts to Planckian radiation at thermal equilibrium in the microwave, you have to check that. And the actual result, which we saw by putting Ecosorb on the silicon plates, is the very bottom. That's an experimental curve. And you see that it reproduces both of the possibilities, the other two, but it looks closer, the second one, than the top one. So we adjusted the interpretation of the data to the second one. Okay, what should we see if we are seeing background radiation, which is SU2 left, versus all photons? Next slide, please. This shows you the top one is the all photons, and the bottom one is, well, it's really a calculation based on SU2. That's assumed to be the background radiation. But we also know that the instrument will also see background radiation from the atmosphere. This is a standard fact about ground-based cosmic background radiation instruments. So what you see in the instrument is a superposition of the two. The end result is the bottom one is what you expect if you have the mixture of atmosphere and pure SU2 left, and the top one is the one what you would see if you have all photons for both. Of course, we have all photons from the atmosphere, but all photons from the background radiation. The crucial difference, I think it's obvious, you have the two peaks, but there's also a center peak. Now, let's see what we actually observe. Next slide, please. Okay, the top two are, the top one, very top one, is all photons. The second one is background radiation, is SU2 left. And the very bottom one is what we see in the actual instrument. You see that small second peak. This data, 2016. Then we observed again. Next slide, please. Okay, once again, top is all photons, second, SU2 left, and the bottom one, there we see the middle peak again. All right, this is 2018. Okay, now, next slide, please. Another observation made in 2018. Again, top all photons, middle is SU2 left, and the bottom is what we see. Once again, we see that middle peak. Okay, next slide. All right, now here, once again, you're getting bored with this. 2019, we observed again, and there's that middle peak again. All right, so it's looking good for SU2 left. Okay, next slide, please. Okay, now in the previous ones, what we had was 3 plates of silicon. The only thing we could do is to vary the number of plates. All right, so the previous one was with 3 plates. Now we reduce the number of plates to 2 plates. Now, interestingly enough, in the 2-plate case, the calculations show that the 2 theories should be essentially to give the same result. The top one is all photons, the middle one is the SU2 left, and the bottom one is the observation. Lo and behold, it agrees with what we would expect from SU2 left, and of course, all photons in this case. Now, we have one other possibility of observations. We can observe through only 1 plate rather than 2 or 3. And the next one will show what we actually saw in that case. Next slide, please. Okay, 1 silicon plate. The top one, all photons. The middle one is the SU2 left field. You see, there is no peak at all in the middle of the graph, and there is 1 little peak for the SU2 left. And what do we see? That's the bottom one. There's that little peak sneaking in again. So, next slide, please. I think it's looking pretty good that the background radiation is SU2 left. But what I want is other observers, I hope to encourage, hopefully with this talk will help encourage other observers to actually repeat the observation. Because remember, you can't trust the result of an experiment until other people have confirmed it. So right now, here's the experiment. I have already published an outline with some of the details of exactly how the instrument was assembled in that Journal of the British Interplanetary Society. What I'm giving you today is all the data. And I think it looks much impressive data showing that the background radiation is SU2 left. Next slide, please. Okay, now I want to mention one other thing. We all know that the background radiation is Planck. This leads people to believe that the universe has to be in thermal equilibrium. And the reason people think that is of the Planck distribution. Remember what Peter Debye did? You're probably not aware of this, that he was the one who created this proof. You've all seen the proof. What you do is you extremize the entropy subject to energy conservation. That gives you the Planck distribution. The point is that that's not the only way a Planck distribution can appear. Planck didn't assume maximum entropy in his original derivation. Now, Stephen Hawking showed that a black hole will evaporate thermally. That is, the black hole radiation will look like a Planckian distribution with temperature defined by the mass of the hole sufficiently far away. But if you look at the derivation Hawking gave, he never once extremized the entropy. He got the Planck distribution purely from the Schwarzschild geometry. Now, in the case of the universe, remember I've already told you that the Bekenstein bound forces the universe to be homogeneous and isotropic, which is to say Friedmann. That forces the universe to have a Planck distribution. I've given the details of the calculation if you want to go through it. In my Reports on Progress in Physics paper in 2005, you can look it up. It's also on the archive. But the point is that seeing it's a Planck distribution is no indication that it's in thermal equilibrium. We know it can't be in thermal equilibrium early in the universe, at the very least. One of the Sakharov conditions is only if the universe is not in thermal equilibrium can we create more matter than antimatter, which is what we observe. So the claim is it's not in thermal equilibrium then when matter was created. It certainly wasn't. And it's not in thermal equilibrium now. It has to be Planck. It is Planck. It's observed to be Planck to an extremely high degree of precision. But that high degree of precision is just measuring that the universe is homogeneous and isotropic to a high degree of precision. Now, let's follow through the final logic of what the universe must be like in the absence of event horizons. Okay, now it implies intelligent life will never die, which is the basic conclusion, the basic assumption, the final entropic principle. How do I get this? Well, how do we actually eliminate the event horizons? Now, the British mathematician Malcolm McCallum proved, in the 70s, that event horizons can disappear near the final singularity only if machine intelligence is present all the way into the final singularity, guiding the universe to eliminate event horizons. So intelligent life has a glorious future ahead of it. Next slide, please. Okay, now eliminating event horizons requires our descendants, which will be artificial general intelligences, their computer power has to increase without limit. Now, there are some problems to overcome in order to increase the computer power without limit. Obviously, we have to turn off the current acceleration of the universe. The Standard Model actually tells us how to do this. Remember, the Standard Model is telling us that the acceleration is due to the vacuum tunneling, changing the vacuum. because of quantum tunneling generating matter rather than the antimatter. So you reverse the process, you will turn off the acceleration. This allows intelligent life. In order to survive, they have to expand out and engulf and seize control of the entire universe in order to guide the universe into the final state. And to do this, they will have to cancel the acceleration on their good time. Effectively, what we will have is we will be approaching in the far future, before they collapse into the final singularity begins, an Einstein static universe phase in which intelligent life gets its act together, gains full control of the entire universe to guide it into the final singularity. Okay, so now remember, I emphasize again, unitarity, this fundamental principle of quantum mechanics, requires there to be some mechanism for turning off the dark energy. The standard model is the way it will, in fact, be turned off. Next slide, please. Okay, now the Bekenstein bound does something else interesting. It tells us that the complexity of a human being is limited. The complexity of the entire visible universe now is limited. All you need is a mere 10 to the 122 bits of information storage in order to perfectly emulate the entire visible universe. That's the Roger Penrose number. He got it right. The point is that if you have sufficient computer power, you can emulate the entire universe, and therefore, in the far future in which the universal Turing machine is being constructed, that is, accessible memory is increasing entirely without limit, you will have plenty of computer power to emulate everything and everyone who has ever lived. Okay, so not only will life survive, individual human beings will be resurrected in the far future, never to die again. The laws of physics require it. If the laws of physics be for us, who can be against us? Thank you very much. Open to questions.
Yeah, thank you, Professor, for your brilliant talk, and it was quite great. I would like to express my sincere gratitude to you for sharing your profound wisdom on both your theoretical and experimental aspect of your work. Thank you very much, sir. So
It's my pleasure.
now I would, thank you. So before going further, so screen share, please. Yeah, so here we can, I would like to just remind our participants to please again submit your questions to Professor. You can click on the link in the chat box to submit your questions, or you can scan the QR code. So we have got few questions. So yeah, so this is question by Bak, Bangalore University, India. He's asking, Higgs fields has weak interaction with matter, but dark matter has no interaction with matter. Hence, how can dark matter be regarded as oscillations of the Higgs field?
No, you're not right there. Dark matter has no electromagnetic interactions with matter. Higgs field, I completely agree with you, has weak interactions, but the Higgs field has no electromagnetic interactions, has no charge. So it will look dark. That's what it's meant by dark matter. It's dark. Doesn't give off light, doesn't interact with regular matter to generate light.
Yeah, thank you, sir. Next question, please. So this is question by Ritvik. What is the quality factor of the FP resonance? And also there is a asymmetry and deep in the FP curves. What is the reason behind that?
I'm sorry, I do not know what an FP curve is, or FP resonance.
I think it's Fabry-Perot resonance, Fabry-Perot cavity, which you, the curves which you saw, I think.
I'm sorry, I just don't understand the question.
Okay, next question, please. So this is question by Kumar Ravi from Swami Vivekananda University. Since both dark matter and dark energy are dark in the sense that they are indirectly inferred, would it be meaningful or even correct to interchange the terms dark matter and dark energy if the historical naming had been different? or is there any fundamental principle of physics that prohibits such an
Well,
interaction?
the dark matter is called dark, and it's called matter. Remember, it's the standard model is lambda CDM. Lambda CDM is lambda refers to the dark energy, and CDM is cold dark matter. Cold because it has zero pressure insofar as anyone can measure it. Now, dark energy means that refers to lambda, the cosmological constant. That means it has plenty of pressure. So it has energy associated with it. That's why they call it energy. Dark because, once again, it does not interact electromagnetically with matter. So that is the reason for the origin of the terms, why physicists call it the dark energy, because it has pressure. It's dark because it doesn't interact with regular matter. It doesn't interact electromagnetically. And cold dark matter because it has zero pressure, looks just like matter, and that's exactly what the Higgs field looks like. Now, one of the slides apparently was not shown, in which I point out that this Higgs field oscillation looks like cold dark matter only if you include the lower order terms in the Higgs field. If you include all the terms, then there's a slight variation, which, depending on the details, which I can't measure, unfortunately, and can't calculate at the moment, may or may not be present. If they are present, what they would do is say that the cold dark matter is not really perfectly cold. It's slightly different from cold, and the end result is that it explains the Hubble tension. As you may know, the Hubble tension arises because if you measure the Hubble constant at the time of decoupling at redshift of 1,000, you get one answer. And you can, if you assume that the evolution of the universe from then to now is lambda CDM, that tells you what the Hubble constant is today. You can compare that with the measure you have today, an atom race. Johns Hopkins University Hubble Observatory says there's a discrepancy between the two. Now, Wendy Friedman in her lecture here says she can't confirm that, so it's an open question. But my point is, in the slide, which unfortunately was left out, is that the Higgs field as the dark matter can resolve that Hubble tension.
Yeah, thank you. Thank you very much, sir. So we will take a last question. Please share the screen. So this question by Raj is, how would Higgs field oscillation dark matter manifest in cosmological data?
One of the ways, and I have a preprint, I haven't published this anywhere yet. The preprint just went up. Look at it. The Hubble tension problem, Hubble tension resolved by standard model of dark matter. One of the ways it would manifest itself is in the Hubble tension, again, assuming that's real. Another way, which I point out, is that you can actually confirm that this is the mechanism by looking very carefully at Higgs boson decays. Higgs boson decays will determine whether or not this explanation for the Hubble tension is correct or not. Again, that's in the technical paper, which is online.
Yeah, thank you. Thank you very much, sir. Thank you for addressing this question with so much depth. And we will conclude for today. And on behalf of Bhaktivedanta Institute and all the audience, we would like to once again express our gratitude to you for joining us today and enlightening us with your words of wisdom. Thank you, sir.
My pleasure. Thanks for inviting me. Goodbye.
Thank you, sir. So, yeah, so this is our tomorrow's schedule. So our first talk will be by Professor John Swartz, California Institute of Technology, Caltech. And he will be talking on very interesting topic, string theory in the 20th century, a personal perspective. And our second talk will be by Professor David Dilworth, US Naval Postgraduate School, USA. And he will be talking a very intriguing and thought-provoking session. He will take a very interesting session on the topic, bubbles and voids versus fancies. Oh my. Our third talk will be by Sri Varun Agarwal, Director of Bhaktivedanta Institute, alumnus of IIT Kanpur, and he will be taking a very interesting session, Cosmology and Consciousness, Search for a Complete Story of Our Universe. So please do join tomorrow with this very interesting talks. So there are a few announcements for today. So there are, as you can see, there are a few publications of Bhaktivedanta Institute, and we move into a segment that transcends the boundaries of conventional thought, navigating the profound intersections of theoretical physics and cosmology. So it's my honor to present these two monumental, books, publications from our Bhaktivedanta Institute. So the first one is about dialogue and expedition into and secrets of the universe, which features legendary Professor Freeman J. Dyson. So this discourse invites us to peer through the eyes of one of the history's greatest visionaries as he unravels the fundamental mysteries governing our existence, covering various aspects ranging from origin of life to astronomy, discovery of numerous planets in the universe, astrocosmology, and many more. So please do grab this very interesting magazine. And the second book publication is about the IQ of our universe, and this is beautiful article written by Dr. Gerald Schroeder, who is an esteemed MIT physicist. So Dr. Schroeder challenges our perception of the cosmos, asking us to consider where this universe itself possesses an inherent intelligence. So together these both works serves as a bridge between rigorous scientific inquiry and the eternal quest for meaning, reminding us that the more we discover, the more we stand in awe of the sublime design of our reality. So the second announcement is about a very interesting video course. So this is a very technical video course, which title is Exploring the Secrets of Our Universe. And it offers a comprehensive 196-minute breakdown of modern cosmology across 5 intensive sessions. So the curriculum focuses on the physics of time, fine-tuning of physical constant, and multi-dimensional nature of cosmic reality. So you can see there is a list of few global researchers. So the first is the article is contributed by Professor Greg Callender, who is in University of California, San Diego, and he is a specialist in the philosophy of physics and logic of time. Second article is contributed by Professor Ram Gopal Uplavri, expert in complex chemical and physical system. And the third video is by Dr. Vignesh Krishnan Kutty from Calibate Technology, Singapore. The fourth is by Professor Manoranjan Sinha, who is a professor in IIT Kharagpur, and he focuses on aerospace engineering and orbital mechanics. And the last one is contributed by Professor Hare Krishna Mohanta from BITS Pilani, and he's expert in process control and system engineering. So this is a very interesting video course. So you can go to our website also. As you can see on the screen, there is a website link. So you can go to the website and please have a look into this very interesting video course. So coming to our conclusion, so these are the timings for our lecture. So tomorrow is Saturday, so please do join at around 10 a.m. in the morning. So the session will start by that time and will end by 1 p.m. So both Saturday and Sunday, the timings will be different. So thank you all. So again, I would like to thank all the audience here who joined us. So please do join tomorrow. Thank you.